image processing engineer and researcher with keen interest in teaching learning of computational skills. She has worked on analysis of endoscopic images, ultrasonic, and MRI. On the behalf of Rajagiri School of Engineering Technology Management, I give a warm welcome to Dr. Sri Lakshmi Sri. Okay, now over to Sri Lakshmi for the speech. Sri Lakshmi will be joining us within 3 minutes. I repeat, I advise everyone to please wait for 5 minutes. She'll be joining us within 5 minutes. Hi, Nisa. Fine, Papa. Can continue.
May I may I now invite Sri Lakshmi to deliver the session.
Hello, am I audible?
Yes, ma'am. You're audible.
Yeah, yeah. Okay, so I'm starting my presentation. So, is my screen is visible?
Yes, ma'am, your screen is visible.
Okay. Good afternoon, all. I'm Sri Lakshmi, Project Engineer at Healthcare Technology Innovation Center, IIT Madras. Today, I'm going to talk about Python libraries for medical image research with an example case study. So the example case study is very relevant in the current scenario and it is very simple, which is the classification of CT images between COVID-19 positive and COVID-19 negative. So here we are using chest CT images, and so the session that I'm going to deliver today is just giving an introduction to Python libraries. I'm not going to give a more detailed information about the Python libraries because the time is very limited. So I'm just giving some introduction to the introduction to some of Python libraries which we can use for medical imaging research. So, my agenda for today is to deliver a small introduction for medical imaging in general, and what is the research and what is the problem statement that we are going to deal today, a small introduction to Python, and Google Colab and coding related to the problem statement. So, the first part is medical imaging in general. I hope you all got a good introduction on medical imaging on the last sessions. Normally, in medical imaging, the techniques will create a visual representation of our body. These visual representations are used for medical intervention and for representation of organs and to identify the presence of any malignancy or pathology like tumor, some foreign object, etc. Before going to medical imaging research, we will talk about general image processing. Image processing is a set of operations to be performed on images to generate a new set of images to extract some information from the images. So the input to an image processing application will be an image and the output will be either another image or some information. Basically, the steps in image processing involves image formation, image visualization, image analysis, and image management. The first step, image formation, involves the acquisition of the image. In medical image processing, image formation is the acquisition of images using modalities like CT, MRI, PET scanning, etc. In the next step, that is image visualization, the image will be visualized and will do some manipulation on the image to get a new output matrix. For example, enhancing the CT image for more contrast, segmentation of the brain tumor from brain MRI images, etc. In the third step, which is image analysis, some measurements or abstraction will be done on images. For example, identification of a particular type of brain tumor from the already segmented brain MRI images. Finally, in the image management step, the processed images will be either communicated or transmitted to some other system or some other person, or it will be stored for further studies and further analysis. I'm sure that you all are familiar with the examples of the very important modalities. The first one is an X-ray image of rib cage, and the second one is the CT or computer tomography image of lungs. In this slide, the first one is the ultrasound scan of the stomach, and the second one is a slice from brain MRI. I'm not going to explain the science behind the acquisition of medical images, which itself will take much time. So, with this introduction to the general or biomedical image processing, I am moving on to the next part, that is Research and problem statement. So what is a research? Now, this is from the point of view of a practitioner involved in biomedical image research problem. Pure academic way will be little more elaborate and can have additional steps. So how we will start a research? We can divide the entire research problem into three major steps. First is the first is the formulation of the research problem, where we will fix our problem statement. The second step is the research activity, where we will try to find a solution to the identified or fixed problem statement. And the final step is to arrive some findings on the formulated problem statement. So, in today's subject, we are going to talk about the Python libraries. The major use of Python libraries will happen in the research activity. For the case study, I myself made a problem statement, and I am going to talk only about the second step, that is the research activity. So, in the research activity, we have to collect the data for the particular problem statement and analyze the collected data and do some interpretation. So here is the problem statement that we are going to discuss today, which involves CT images. The problem is to make a model that will classify the given chest CT image into either COVID-19 positive or COVID-19 negative class. I took this problem of COVID-19 challenge from All Grand Challenges, which is a platform that hosts medical imaging challenges and hackathons. In the Grand Challenges, you can see many problems to solve, and the best solution will get good rewards and a platform to get to publish their solution. I'll just show you the Grand Challenges site to you. This is the site for medical image Grand Challenges. Here you can see many medical imaging challenges which you can use for your research. So this is the problem statement that I have taken as a case study for today, which is the CT diagnosis of COVID-19. You can refer to this location. I added this link, the link to the Grand Challenges in my last slide. You can go there and see many medical imaging research challenges here. Okay, so what we have to do for this problem statement? Classification of lung CT images. So, we need to develop a model or solution through our research, which will take the CT images input and classify the input image into either of the two classes, COVID-19 positive or COVID-19 negative. What is our model? How we will develop the model through our research? I have already told that the input to our model will be CT images and the output is a class positive or class negative. So the model is the solution that we are going to develop through our research. What are things we require to develop the model? We need a set of CT images which are already classified into COVID positive and COVID negative. Here our problem is a classification. So what is a classification problem? Generally, classification is the process of grouping of data into available classes with our prior knowledge. For example, we know how a cat and dog looks like. So we can easily classify the images of pets into cat and dog classes because we have prior knowledge or prior information about the structure of cat and dog. But how we will teach a software to classify a cat and dog? We need to teach the software the features or the structure of the cat and dog. Likewise, here we need to teach a model to classify the CT image into COVID positive or COVID negative. So, in order to teach or in order to make a machine to learn, we need to use machine learning algorithms or deep learning algorithms. So the libraries that we are going to use for machine learning or deep learning, I will show in the next session. Okay. So we'll come back to our research activity. So we found our research problem, right? Now we are going to perform the research activity. So the first step of the research activity is collecting data. In the medical image research problem, we need to collect the image data which will be suitable for our own problem statement or our own research. There are many publicly available data sets like brain MRI, brain CT, lung MRI, etc. Some of the datasets are free to use. On these publicly available datasets, some are free to use, some may require registration and licensing, some are paid dataset. If we didn't find any publicly available dataset for our own problem, we may have to associate with hospitals or labs to collect the required dataset. Most of the medical images will come in special image format like DICOM, NIFTY, etc. Not in normal image formats like .jpeg, PNG, and all. So we need to understand the standard format of the obtained dataset and convert the images into the specified format or the format that we are familiar with. Some publicly available datasets are already converted into .png or .jpeg, so there may not be need of any other conversion required. We'll talk more about the standard medical imaging format in the next session. So in our problem, the dataset is already given in the challenge website. We just need to download it. And the image format is .png. So this is very easy to use as a normal image. We don't need to use many libraries, many medical imaging libraries here for the conversion or standard image, standard format analysis and all. We can directly use general image processing software also here to perform the classification. Okay, once the data is collected, the next step is analyze and interpret the data. So, in the analyze and interpret data step, we can further divide the entire step into 4 sub activities. First is an image pre-processing, then an image analysis, then quantification and findings from the quantification. First step is image pre-processing. The pre-processing or filtering step is for improving the image quality. What is image quality? We used to say that the images is of less contrast or too bright or image is too noisy, right? So these are our image quality. In an image with better contrast, we can see more details. Too bright or too dark images may not have much information. Some images may have unwanted information called noise. All these scenarios I will show through example images. Now, how we will improve the image quality? First, we need to visualize the data. Then we need to analyze the data for the presence of any quality issues. Then we need to decide on certain image processing techniques to perform quality improvement. This is an example image from the COVID-19 dataset. For me, the brightness and contrast is not having much issues, but you can see in the gray area some grains kind of structure, which are unwanted information. Here also you can see. So one problem associated with this data is noise. See, in this slide, the center image, this is the actual image. And this is a darkened version of this image. And the last one is a more brightened version of this image. In these two images, many details are missing. For example, in this area, many small details are missing because this image is a dark image. Similarly, here in this image, in the gray area, it's very difficult to identify the portions and all. So, in terms of brightness and contrast, the first and last images of not a good quality, and the center image, which is the original image, is of having a better quality. I'm not saying that it is a very good image, but compared to the darker and brighter version of the images, it is of an average quality. So currently in our image dataset, the problem that I see is noise. So the image processing technique or image pre-processing technique that I have to use here is noise reduction. Next step is image analysis. Once the image pre-processing step is completed, we need to do some image analysis. Some example image analysis techniques are segmentation to extract some pathology, classification to classify the images or the segmented portions, and registration of images into multiple views, etc. Here in our research problem, the image analysis we need to perform is a classification of images into 2 classes. It is a binary classification problem. Here our image analysis method that we are going to see is a classification. So Once the image processing, image preprocessing and image analysis part is over, the next step that we need to perform is quantification of a classification algorithm or quantification of the research, and finally the findings from the quantification. Generally, classification algorithms are quantified using a confusion matrix. I'll explain this in very detail when we deal the problem statement through our codes. So now we are going to move to the next part of the session, which is an introduction to Python. I hope almost all of you are familiar with a very simple programming language or very simple programming and algorithms. Even if you all are not much familiar with coding or programming, the Python is a very simple language, very simple, easy to understand language. I'm not going to give any coding or anything here. I'm just giving an introduction to Python. So it is a very general purpose programming language which is very easy, and the rules or syntaxes of the coding is also very simple. It's like a normal English language only. And the debugging, that is the identifying the issues related to the codes and functions that we have written, is also very easy. So how to install Python? For that, you need to go to the python.org website, and you need to download the required Python version or required Python for the operating system that you are using. So this is the python.org website. In this downloads, you can see the Windows, Mac OS platforms. So you just need to go to these links and download the installer. In Linux, the Python will be already installed, and you don't have to download the Python installer. But for writing Python code, you need an IDE or editor to write Python code, and you have to use a command line programming to compile the code. These all are very simple and easy to install. Even if you are spending 1 hour or 2 hours, you can easily understand the working of Python. Another feature of a Python is an IPython Jupyter notebook, which used to come with Python environments like Conda and all. It's an interactive computation environment. We can use Python Jupyter notebooks as command line programs or Python programs, or we can code also in Jupyter notebook. So a command line program means we know how to use either Windows command prompt or Linux or Mac OS terminal, etc. Right? Like that, we can just give instructions in Jupyter notebooks, that is interactive Python notebooks, to execute certain tasks. So what if you don't have a Python installed in your system? Or what if you don't know how to write in an IDE editor? There is a solution for all this. So all of us have a Google account, right? Most of us will be having a continuous access to internet or Wi-Fi, right? So if you have a Google account and if you have a continuous access to Wi-Fi, there is a solution to get IPython Jupyter notebook without installing anything to your system. That is Google Collaboratory. The short form is Google Colab. It is a free notebook environment that we can run on internet on cloud. No configuration or no installation is required for running Google Colab. It is very easy to share. The Python codes that you are making, you can simply share with a single click. I've already told that for the classification problem, I am using either machine learning or deep learning algorithms. These machine learning and deep learning algorithms are high processing algorithms which require systems with the graphical processing units, which are very expensive. But if you are using Google Colab, you will get access to GPUs freely. The only thing you need is a Google account, and you need to mount Google account with Colab. I'll show you how to mount that. Whatever the notebooks that you are making, whatever the codes that you are running on Python notebooks, it will get automatically stored in your Google Drive. You don't have to save anything. Whatever the things that you are writing, it will get automatically synced with your Google account. So how Google Colab look? This is the link for Google Collaboratory. Once you click in this link, you will be directed to a window like this. This is the Google Collaboratory window. There is a first tab called Welcome to Collaboratory. Once you go to this link, you will be able to see many examples or how to code Python, coding collaboratively, many introduction and many simple tutorials you will be able to see here in Welcome to Collaboratory. Under Welcome to Collaboratory, you will be seeing all the Python notebooks that you are created. So IPYND is the extension for Interactive Python Notebook. Whatever the notebooks that you are creating, it will come under this Welcome to Collaboratory or come beneath this Welcome to Collaboratory tab. If you want to make a new notebook, you have to go here and press on this new notebook. So a new notebook is created. The name of the new notebook is untitled 2.ipynd. You just need to click here and change the name whatever you want, so that your IPython notebook is ready. So you can see a number 1 over here, and this is a cell where you are writing your code, and when you wanted to run that code, you just need to press this play button, or you can just simply press Shift Enter. Now we will move to the Google Colab and the Python libraries. So I'll be moving to Collaboratory, and I will very rarely use slides now. So the Python libraries that we are going to talk about are the NumPy, which is a general Python library, OpenCV and Matplotlib, which is used for image processing and image visualization, SimpleITK, MedPy, PyDicom, which are medical image processing libraries. And finally, I'll give an introduction to PyTorch, which is a machine or deep learning library. So we will see first how to mount Google Collaboratory, how to mount our Google Drive to Google Collaboratory. So this is the site that I showed. That this is the basic first page of Google Collaboratory research. Here I am. I said that in Welcome to Collaboratory, you will see many tutorials on Collaboratory and Python. So I wanted to make a new notebook. I will press this new notebook tab so that a new notebook will be created. It will take little time. Then once the new notebook is ready, first I'll change the name of my notebook to a name that I need. The next step is mounting Google Drive to Google Collaboratory. It's a very simple step. So it's actually we are giving access to our Google Drive to the Google Collaboratory. This is just a 2-line of code. Every time when we are running the Collaboratory, we need to perform these 2 lines of code. This is the Google code, or this is the Python code for collaborating Google, for mounting Google Drive to Google Collaboratory. But you don't have to by heart those steps. For getting that 2 steps, you need to go to this Tools tab, Command Palette. Here you search for mount. We get a mount drive. It will ask for permission. So you give permission to connect to Google Drive. These are the 2 lines for the Google Collaboratory mounting, which is very simple to get, and there is no need of any by hearting. Once this line is ready, you just need to press either Shift Enter or press this play button. It will take a little time because it is accessing the Google Collaboratory using internet. So it will take 2 to 3 minutes. So we'll wait for the Collaboratory to get mounted. Okay, so this will give a URL. We have to go to this URL. Then we need to give authorization to the account, Google account, and we will allow the access, and then there will be a code which is called as authorization code. In order to copy, we need to press this two squares and we will paste the authorization code here in, and we'll press enter. So the Google Collaboratory mounting is over. Once this Google Collaboratory is mounted, we need to go to our drive location where our files are getting saved. For that, first we need to change our directory to my drive. So I hope all you are familiar with the cd command, which is change directory. So now the current working directory is my drive. In my drive, I made a folder called RSET, in which I have all the data that I am going to present or that I am going to deal with today. So I need to move to this location. So I am moving my current directory to RSET using the same command cd. If you are not familiar with cd and all, you just need to Google it. It's a very simple command lines. You will understand it from Google. So these are the basic steps that we require to run a Google Collaboratory. Now we will move to our research problem, which is COVID-19 classification. So this is my code for the basics and basic steps, that is image pre-processing, visualization and image pre-processing. The other things I will show in another IPython notebook. The initial 3 steps, I'm not going to run these steps because it will take time. So the output is already available under the code. So I'll show you the output. If I am running each line of the code, it will take time. So the first 3 steps I have already done here. In Google Colab, we can add text also. If you press this text button, we can add here, we can type also. So I have already told that we are going to deal with NumPy, which is a general Python library, OpenCV and Matplotlib, which is used for image processing. Symbol ITK, MedPy, PyDicom is for medical image processing libraries, which is actually not required in the current problem statement, but I'm just showing how to use those libraries also. And machine or deep learning libraries like PyTorch, Skitlearn, and TensorFlow. I'm showing introduction to PyTorch only, but I'll just I'll talk about simple applications of Skitlearn and TensorFlow. So as we have already discussed, the second step of a image processing or biomedical image processing is analyzing and interpreting the collected data. So where is our data? The data is already available in the challenge website. So in data info, there is a location, Git location, from where we can get the images data set. So I have already downloaded this location and I have saved all the data in my drive. This is the data CT COVID and CT non-COVID, which are already labeled and we are going to classify. And using these data sets only, we are going to train the train our classifier. I'll show you some example images. So this is our images that we are going to use here for the classification. These are COVID images. Actually, I can't say these are COVID images. These are the lung CT images of people with the COVID-19 diseases. And there is another folder which is CT non-COVID. Again, in this folder also there are images of the chest or lung CT images of patients who are not having COVID-19 diseases. Okay, so once the data collected, the next step is analyzing and interpreting the collected data. I have already told that there are 4 steps for that: image pre-processing, image analysis, quantification, and findings from the quantification. So the first step is image pre-processing. For image pre-processing, I have told that we need to first visualize the image, and we need to identify the problems with the image, and finally we need to perform some image processing operations to remove that quality issues. For image visualization, I am using OpenCV and Matplot Python libraries. So from here onwards, we are talking about Python libraries, which is the actual topic of today. So OpenCV and Matplotlib are the Python libraries that I am going to use for image visualization. Okay, I'll share the notebook link. Sorry. So I'll share it at the end of presentation because I don't know to whom to share this code. Okay, now we were talking about image visualization. So here I am using OpenCV and Matplotlib for image visualization. OpenCV is for loading the image and for image pre-processing operations. Matplotlib is for plotting the processed image or the loaded image. And OpenCV uses another famous Python library called NumPy. I hope almost everyone are familiar with the NumPy. So OpenCV uses or OpenCV loads the images as a data type called NumPy array. Again, if you are not familiar with this terms, you just need to Google it. It is very simple to understand. And so these are the 3 main libraries that I am going to use for image processing. It doesn't mean that these are the only libraries for image processing. There are some other libraries also, but these are the libraries that I am familiar with. I'll share the notebook at the end. Now, once these libraries are there, we need to install it to our Python. In Google Colab, you don't have to install any of the libraries because almost all the famous libraries are available in the Google Colab. You don't need to install it. But if you are using a system or if you are using a normal Python, you need to install all these libraries using Python package installer. That is pip. So these are the pip install is the command for installing these libraries. Since the libraries are already installed in the Colab, once you run this, you will get only requirement already satisfied because all these are already installed in our Google Colab. Only the libraries which are very rare is not available with Google Collaboratory that I will show you later. So once these libraries are installed, you need to import all the Python packages. So import is a function for importing the function or functions or methods from the Python libraries or Python packages. So here import CV2 means we are importing the OpenCV. OpenCV's package name is CV2. Similarly, we are importing matplotlib.pyplot. So pyplot is a function for plotting in the matplotlib library. So we are importing matplotlib.pyplot as PLT. So we are importing this library and we are not going to use this big name. We are using the name PLT only, and we are importing numpy as np. So these are the first importing functions for the packages that we are going to use. Next, we are going to visualize the image. For visualizing, first we need to read the image. For reading the image from the path, we are using the function called imread from CV2, that is OpenCV. So this is the path of a single image from our data set. We are just giving this path and we are reading the image and we are showing the image using matplotlib as plt.imshow. I'm not giving further details of these functions and all. I'm just giving some introduction to the library only, so I'm not going to give detailing about the coding. Okay, so I'm just visualizing the red image, which is IMG. So this is the image uh, of this is a sample image from our data set. We have visualized the image now. So from the slide itself, we have visualized the image, and we came to a conclusion that the problem associated with this image is noise. So the only pre-processing method that we are going to perform is noise removal. Before doing the noise removal, we will see what if, so I told you that this is a PNG image. So suppose if in our problem the data set is of standard medical imaging format, how we are going to view those images? So I'll just show you that also. Then we will move to the image pre-processing part. So there are many standard medical imaging formats like DICOM, NIFTY, NRRD, MHA, etc. Out of this, the most common medical imaging standard formats are DICOM and NIFTY. DICOM is the international standard to store medical images. The expansion of DICOM is digital imaging and communication in medicine. So in these medical imaging formats, in addition to the image data, it contains some meta information also, like patient details, examination details, modality details, rate of examination, etc. So in DICOM image, there is patient details, which is gender details and which age details. What is the problem? What is the exam? What is the examination that we are doing? What is the series we are doing? Many meta information will be available in the DICOM format. A similar data format is NIFTY, which is Neuroimaging Informatic Technology Initiative. This will represent the volume of an organ with stacks of image slices. DICOM may be a volume or a single image slice, but NIFTY will be always stacks of image slices. So the meta information will be there in NIFTY also, but patient-related meta information will not be available with the NIFTY images. This NIFTY image will always represent the entire set of images. NIFTY is most commonly used for MRI images. In most of the cases, CT and all we will see DICOM images, but rarely NIFTY is used for CT images also. But mainly this NIFTY image is developed for MRI imaging, that is magnetic resonance imaging. So how we are going to visualize these kind of standard medical images? So the Python libraries that I am familiar with for standard medical images visualization are Symbol ITK, PyDICOM, MedPy. Symbol ITK is an ITK platform or ITK wrapper for Python. So actually it is available for 8 different programming languages like Python, C++, Java, etc. Almost all the other medical standard imaging formats like DICOM, NIFTY, NRRD, MHA, etc. We can view or visualize or process using Symbol ITK. So this when you see the Symbol ITK for the first time, you will feel like it is a very complicated library. It is not simple as other Python libraries like OpenCV and all. So there is a good tutorial in GitHub with the Symbol ITK notebooks. So once you go through those Symbol ITK notebook pages, you will get a clear idea of Symbol ITK. Unfortunately, I forgot to put the link for that notebook that I will share. Okay. The next one is PyDICOM, which is a Python library for the analysis of DICOM images. It is also very simple as OpenCV and all, but it is just used for only DICOM. You can't see the NRRD, MHA format using PyDICOM. And MedPy is also another Python library for this medical imaging viewing and saving, processing, etc. So this is also very simple to learn. So, but when you see or when you start learning these libraries, I hope Symbol ITK is the one which is little complicated compared to PyDICOM and MedPy, but you will get the functions or the inbuilt functions in Symbol ITK is more advanced than PyDICOM and MedPy. So similarly, we will install this all 3 imaging libraries using the pip, which is Python package installer. generally in collaboratory, these three will not be already installed. You have to install these three libraries every time you are using the code. Every time, whenever you are using this notebook or the notebook in which these are installed, you need to install it after mounting the Google Drive. So in my thing, I have already I ran it twice, so the requirement is already satisfied. If you are running it for the first time, you will see a bar for installation. Now, once this library is installed, I'll use these libraries to show you how to visualize the images using this libraries. So this is a library. This is MedPy for visualizing the nia.gz is the extension for Nifty image. This is how MedPy is used for displaying a Nifty image. I'm not going through the line by line coding and all. Here we can see the size of the image or the shape of the image is 512 cross 512 cross 129. That means there are 129 slices of MRI, sorry, CT images of each slice is of size 512 cross 512. So I am here displaying the 120th slice from the Nifty image dataset. So it's very simple. This image header is the metadata that I had talked about, but I'm not showing the image header because it may contain sensitive data like patient details and all. Normally, in public datasets, this image metadata, patient-related metadata may be removed for data sanitization and for the public problems. I'm not showing what is the metadata here because it contains some patient information. Similarly, this is how we use a simple ITK for visualizing the same Nifty image. Here we are using the read image function from symbol ITK and we are giving the same image name. So it have an extension nia.gz, that means it is a Nifty image. And we are converting it in, we are doing a get array from image function here. This is for extracting the image data from the Nifty image. Because this SITK even contains the metadata also. So I want to display only the image, so I am using a get array from image function here. So we will be so here the format of the volume is different. Here first the slice number, then the image height, and then the image width. So while displaying it also, I will give the first image slice number, then height and width. First image slice number, height and width. So when you see these two images, you can see there is a difference in orientation of the images. Even if you are visualizing the same image, there is an orientation of the image. This orientation will be different for different medical imaging libraries because it is taken from the image metadata. Here we need to change the orientation according to the image this image orientation and all. According to the image metadata, we need to change the orientation. Those things will be little difficult to explain in this small session. So from symbol ITK notebooks, you can directly understand how to use those orientations. Finally, I'm using a PyDicom file to read a DICOM image. DICOM image is the most common medical imaging standard format. So I have used another DICOM file which is having an extension of DCM. I'll read that DICOM image using DCM read, and I'll display that DICOM image using Matplotlib PLT I am sure. But here we are taking a single slice of DICOM image only. There is no volume, only a single slice is available. So you don't have to specify any slice number for this. Okay, so I just gave a small introduction to Python libraries for visualizing medical images. Now we will come back to our program. So we visualize the our dataset image, and we know that we need to remove the noise. There are many noise removing or denoising algorithms available in OpenCV, like median filtering, Gaussian filtering, Many filtering techniques are available in OpenCV built-in functions for removing the noise. So in my research, I have applied all the almost all the noise denoising filters from OpenCV, and what I understood is that this denoising algorithms are removing noises, but some small details from the image is also getting removed during the this denoise filtering application. I'll show you. There are some small details inside this portion, right? These details are also getting missed during this denoising filters. So the best denoising filter that I found by trial and error method by applying different filters is the bilateral filter. Bilateral filter is a smoothing filter with some smoothing or noise removing filter with some advanced maths. I'm not going to say any math of this bilateral filter because it is a very huge math behind this bilateral filter. The advantage of bilateral filtering is it will reduce the noise while preserving the image edges or small image details. So it is a best denoising filter for our application. For current problem statement, this bilateral filter is a good image pre-processing filter. We have to give some values. These values are smoothing factors alpha and beta. Those you will get when you go through this bilateral filter math and all. So this is the image after the bilateral filtering. But now we can't say whether this bilateral filtering has removed the noise or not. So we are going to compare this image with the original image. Here, this image, the first image is the original image, and the second one is the filtered image. Here you can see the grains over here is removed in here. That is in the gray region clearly. You can understand that there is a removal of the grains. So this is the image pre-processing part that I have done for this current COVID-19 research problem. I have applied this bilateral filtering to all the images in my drive, and I have saved all the filtered output already in the drive. So from the next step, you are going to process the already bilateral filtered images. So the image pre-processing, that is the first step of the research activity, data interpretation and analysis is over. So now I am going to a new notebook where we are proceeding with the next steps of my problem statement. Again, here in this first three steps, we are mounting the Google Collaboratory. We are mounting the Google Drive with our Collaboratory. So these steps are same. I'm moving to the RSCT folder, and we'll do the image analysis and the further parts. So in the image analysis part, see in these two images, the first one is a COVID-19 image and the second one is a the first one is a normal image and the second one is a COVID-19 image. Almost every structure is similar when we compare these two images. There is no single feature which is visually making the COVID images different from normal images. So we can't do any basic image processing methods to classify a normal image from a COVID-19 image. So we need to do some analysis, some further analysis. For that, we are going for machine learning first. In machine learning, we need to extract some features from the parts of the lungs or some parts from the gray matter, etc., to classify the images using classic machine learning techniques like SVM and all. Since we don't find any structure or parts from the image we can't do for feature extraction, we need to give the entire image to a neural network, which is a deep learning portion. Deep learning is a part of machine learning, which uses neural networks, which works like human brain for classification, recognition, etc. So deep learning itself is a vast subject. So I'm not going to give any information about deep learning. So by using deep learning, we are making the system to learn to classify our COVID images into COVID positive and COVID negative. now most of you are having a small info or small idea of deep learning. So I'm not going to give any much introduction on deep learning because it is a very vast subject. The deep learning library that I am used for this project is PyTorch. There are many deep learning libraries for Python like TensorFlow, Keras, Theano, Caffe, etc. But the why I took this PyTorch is the one that I am more comfortable. There are people used to say that TensorFlow or Keras are much easier than PyTorch, but most of my work I have done using PyTorch. That's why I chosen this deep learning library, PyTorch. It is an open source machine learning or deep learning library. It have many neural networks which is already developed, and it is most of the famous or common networks are already available as built-in networks in the PyTorch library. And I have already told that OpenCV uses NumPy array data type for representing images, but PyTorch uses multi-dimensional arrays called tensors for calculations. The data type of images will be tensors in PyTorch. Don't if you don't have any idea about this kind of things, don't be in tension. There are many tutorials available online for PyTorch, which are very simple and which are very easy to understand. Okay, so the library that I am using for making my classifier is PyTorch. So Torch is a PyTorch library, and I am importing PyTorch and related libraries here. In addition to PyTorch, you need to install Torch Vision also. Torch Vision is another Python or PyTorch library which is used for loading the image to perform some transformations, image processing operations, image normalizations, etc. Similarly, Torch Vision have a set of datasets which are very common. That is like there are datasets like CIFAR10, which are very famous image processing datasets, ImageNet, etc. All these datasets are readily available in the PyTorch. We just need to invoke those datasets if we wanted to use those datasets in our research. So all these portions we are not don't worry about all these things. These are some other libraries, Python standard libraries for analysis and all, for further for data analysis and all. So somewhere it is getting used, so it is used. And I'm not going to say much details about the networks. So these Torch utils, Torch, this Optim and all related to the deep learning neural network algorithm. So when you go through those kind of algorithms, you will come to know what is this optimization and all. So after importing all these libraries, when I see the images from the dataset, these are of very these datasets are with a variation. Their sizes are not normal, their intensity ranges are not normal. So we need to perform some operations to normalize those images into standard forms. That is, we need to center the mean of those images into a particular mean or an average value. We need to resize the image to a particular size. We need to normalize the intensity values in a particular range and all. So normal images are in the range of 0 to 255, which normally for deep learning we will normalize it into 0 to 1. But if it is a standard medical imaging, the intensity ranges will be very vast. Like negative values will be there, positive values will be there, decimal values will be there and all. So in that cases, the normalization is a very important step. Here it is not that important because all images are of .png format. All are in the range between 0 to 255. So we just need to divide every pixel by 255 to bring it into the range 0 to 1. So how we are going to do this normalization or standardization? For that, we are using the library PyTorch Torch Vision function transforms. First, we'll normalize the data into a centered mean. These mean values that I have given and the standard variation that I have given is the average value of the entire data set, average mean of the entire data set and average standard deviation of the entire data set. We will bring all the images with the centered mean, and then we will perform a resizing operation So we'll make all the images to a size of 256. Then we'll do a random resize crop to remove the border and a random horizontal flip. This will be applied only to certain images. Randomly, it will choose some images and it will flip the image. Then that is for improving the dataset. The horizontal flip is to improve the performance of the dataset and to give more accurate classification even if the image is flipped also. And we will transform the image to a tensor data type and we will do the normalization. So this is the train transformer. I have told that we need to teach the machine learning model or our research model to classify the COVID-19 and COVID-19 and normal cases. In order to that, we need a set of labeled dataset. I have told that. But in that training dataset, we need to divide it into train data and validation data. Train data, we will all train data we will use for training the model, and in order to check whether this training is good or not, we will validate the model using a set of validation data. And if the validation data performance is not good, again we will retrain the data. So this is a step that we are going to do in a deep learning algorithm. So how we are going to do this data set splitting? So dataset splitting is partitioning the whole dataset into two sets, training and validation set. And in the training set, we use 70 to 80% of the total dataset. And in the validation set that we are going to validate the training, we will use only 20 to 30% of the images. Based on the performance of the validation, we will retrain the model. We need one more set for our research, that is test set, test image set. This test image will not be a part of the training set. It is a completely different data set which is unknown to the model. The performance of the model on the test set is the actual performance of the model. That is how the how the model is classifying the test set. How accurately the model classifies the test set is the performance of the model. So how we are going to split the data? Either we can visually analyze each images and we can divide data in a uniform manner, or we can use Python libraries for data splitting. Each machine learning or deep learning libraries have their own data splitting functions. In PyTorch, we have a function called a random split, which is used for splitting the data sets. We can specify the percentage of data splitting. Here I said 70 to 80% we will use for training set, 20 to 30% for validation set. So here we need to specify the percentage of data for splitting. So the random split function randomly split the whole data set into the specified percentage as training set and a testing set. But fortunately, in the COVID-19 dataset, the data splitting is already provided by the challenge website. So we know how to split the dataset, and they provided the dataset in a splitted manner. So the total number of images in our dataset is 746, out of which 397 are COVID positive, and 349 are normal images. In the given dataset, we are having 425 training images, out of which for 199 are COVID positive and 234 are COVID negative. Then 118 validation images, out of which 60 are positive and 58 are normal images, and 203 test image, out of which 98 are COVID positive and 105 are COVID negative. This is our data set. So here we don't need to use the random split to split the data set because the data is already splitted. Okay, this is the starting of our COVID-19 deep learning classification. Here we are loading the data loader is used for loading the training set. So the train set is obtained by giving the directory of the data split and the image directory. And explaining all these functions will take time. So I'm just giving an insight that data loader is used for loading the training set, test set, and validation set. I'm just printing here the length of the training set, validation set, and test set to confirm whether we have loaded the data correctly or not. So here I got 425 train set, validation 118, test 203. I will check whether it is correct or not. Okay, 425 training, 118 validation, and 203 test image. So the data loading is proper. So this is the one of the major part of the deep learning research, which is data loading. I have loaded the data correctly. Now I'm going to train the model. I'm going to train the model using deep learning algorithm. So I am training a model to classify the image into COVID positive and COVID negative. I'm using deep learning neural network to classify the images. So the algorithm, neural network algorithm will be little actually deep and little difficult to understand. So I'm not going to explain the algorithms. I'm not going to explain the algorithms. The neural network algorithms will, what they are doing is, they are having some weights. So the algorithms will run to improve the weight for a better classification or better learning of the classification. So this is a training part of the algorithm, and in the validation what we will do is we will test the validation data with the model, and from the model quantification or the classification quantification we will improve the model training. So what are the quantification for validation, or what are the quantification for classification? So I have already showed you this slide. What is a confusion matrix? So the classification algorithms are quantified using confusion matrix. So confusion matrix is a table used to represent the performance of a classifier. So there are four parameters in a confusion matrix. So the top row, top row of this confusion matrix is the prediction, and this row is the this column is the actual class of the image. For example, if a single image, if an image is positive, actually COVID positive, and the classifier predicted it as a COVID positive image, it is a true positive image. Similarly, if the image is normal and it is predicted as normal, it is true negative. So the true negative and true positive are the correct predictions. And if the image is a positive image and predicted as a negative image, it is false negative. And if it is a negative image and predicted as a positive image, it is a false positive. So false positives and false negatives are wrong predictions. So from these confusion metrics, we need to make many measurements. The basic measurements that we are using are accuracy, sensitivity or precision, and specificity or recall. So accuracy is the fraction of positive accuracy is the fraction of correct prediction to the total number of images, and sensitivity is the probability of correctly reporting an abnormality. Specificity is the probability of correctly reporting that no abnormality is observed. So these are the quantifications of a classification algorithm. So based on these quantifications, based on the values of accuracy, sensitivity and specificity, we will validate the model. We will say that the training is a good training or a bad training, and according to that quantification, this training will move into, if it is a good training, it will move into one direction, and if the training is not good, it will move into another direction. And there we have to specify a number of times, that is called epochs, how much time we need to perform the training and validation. So suppose if I give 300 epochs, 300 times the training will happen. Each time the validation quantification will be doing, and based on the validation quantification, we will do the training of the network. So once the training is over, we will do the testing. Testing is just evaluating the model. So how we are going to evaluate our model is, we'll calculate those parameters, those true positive, true negative, false positive and false negatives from the network or from the prediction, and then we will say that this model is having this much of quantification, or this much of accuracy, this much of precision. So whatever the result of a validation, we will not say that it is a model accuracy. The model accuracy or model precision or model recall is always the quantification from the testing phase. So in the testing phase, the images that we are using are completely unknown to the model, and these images we will not use for training or validation. So In this research, in my research, sorry, I have went through different networks. In my research, I tried many networks to classify the image. I tried DenseNet, ResNet, all versions, DarkNet, a recent network called COVID DarkNet, etc. Almost all are, except COVID DarkNet, almost all are available in the PyTorch. So COVID DarkNet is available for TensorFlow. I converted that TensorFlow code into PyTorch code, and I have done some more classifier also as a trial and error method. I have done. I have spent much time on this network classifiers, and finally, the one which I was satisfied, or which I felt as a very good classifier, is a network called EfficientNet. EfficientNet is a very comparatively recent network. Fortunately, this EfficientNet is also already available in the PyTorch platform. So I'm installing the EfficientNet PyTorch, and I'm importing the EfficientNet network from the PyTorch EfficientNet PyTorch library. So another library that I'm going to use here is EfficientNet PyTorch library. This EfficientNet PyTorch library is a pre-trained network with a base weight B0. There are 7 different EfficientNet libraries. In this research, actually not in this research, in today's session, I have used B0 EfficientNet. So in my research, this is not the actual network that I have used. It is another EfficientNet weight with some modification to the network. But today I'm not allowed to present it here because that is under evaluation. So I'm not showing the output of the actual my research, but this is one of the best network that I have seen. So I have used this model EfficientNet, and I have trained the network. Once you are doing the training, I gave 300 as the epoch or iteration number. So this training will happen here 300 times. I am not able to run here because this training itself will take 2 to 3 hours. When we are doing an online training or something, we are not able to do any deep learning training because of the time constraint. So every time, every iteration, here you can see predict. Every iteration, the prediction will happen, the validation prediction will happen, and then the average accuracy will be calculated. And in every 10 step, so I gave 10 as a validation number. So that means every 10th iteration, all features will be calculated. That is false positives, false negatives, everything will be calculated in every iteration. So this is epoch number 208. So in 210, all the quantification will happen. So in this 210th epochs, all this testing or validation will happen. In the validation step, all the true positive, true negative, false positive, everything will be calculated, and an accuracy of the current step will also get calculated. Based on this accuracy and based on these features, the training is improved. The training step will be improved based on these values. Likewise, the 300 iteration will be completed in the entire training process. So after 300 iteration, we will get a final average accuracy, which is nearly 75 for this thing to 70. So this is the final accuracy. Here you can see the average recall. Recall is actually the sensitivity, specificity, that is 70%. Precision is 77%. So this precision and recall, actually, they are the general terms, general image processing terms. So when we are using this medical imaging research, we need to say it as a specificity and sensitivity. So once this training is completed for 300 epochs, we get a good model which we will be testing in the next step. So here we will test the performance of our model. We will calculate that training, true positive, true negative, etc. So this is the This is how the confusion matrix is formed, and we will print the parameters. So you can see that here true positive is 81, true negative is 85, false negative is 17, false positive is 20. I'll show you this in more detail in slides. So here we can say that 81 images which are positive is classified as positive. 85% or 84% of images or 85 images actually, sorry, 85 images which are negative is classified as negative, and 17 and 20 images were false prediction. From this, we'll calculate the accuracy, sensitivity, and specificity. So here we can say our accuracy is 81%, recall is 82%, precision is 80%. So the training and the model testing and the quantification is over. Now we need to say some findings from our research. So the entire research process is over. So we'll get some findings, and after this research, we can say that EfficientNet is a good classifier network for COVID-19 image classification with 81% of testing accuracy. Now, whether this is a good network or not. For that, again, we need to go to the literature survey. We will see the performance of all the existing networks, and if the highest in the literature survey is not more than 81%, we can say that this is a good solution or best solution. But if the 81% is not enough, it is not the highest accuracy, we have to do again the steps from the beginning to improve our network. So in this COVID-19 challenge, when you go through this COVID-19 challenges, you can see the performance or the testing accuracy is above 90. 93% was the highest accuracy that you saw in COVID-19 challenge. The actual accuracy I got in my actual research is 96%, which is using EfficientNet only, but with some modification, which I am not allowed to present here. So, as an example, I took this EfficientNet B0, which is giving an 81% of testing accuracy. The finding is that the EfficientNet is a good classifier, but not is the best classifier as in the challenge. So I hope you all got a little introduction for the Python libraries that we can use for the research. I know that you didn't understand how to use those Python libraries because of the time constraint. I just explained what is those libraries and how to install those libraries and all. I am sure that you are having doubts on how to use these Python libraries. But I can say that these Python libraries and Python coding is very simple to use, and there are many tutorials available for all the libraries that I have used in today's things. You just need to Google it, and you will get plenty of information on the internet, and which are very simple, which you can learn in a single day also. In OpenCV, Simple ITK, everything you can learn in a single day. So it is not a big task. So I hope you all got a good understanding of Python medical imaging symbol research and the libraries that we can use for Python image processing research. So these are some external links for Google Colab, all ground challenges, CT COVID-19 challenges, etc. So you can go through this links, and if you go to the all grand challenges, you can see many challenges and many research questions. If you are interested, you can work on those challenges, and if you got some good or best result for the challenge that is in all grand challenges, which are best solutions or good solutions, you may get a platform to publish your work, and you may get a chance to get some good amount rewards also. So CT COVID-19 challenge is an ongoing challenge. You all can participate. It is very simple, and this is classification is always the simplest challenge. So you can go to this COVID-19 challenge and participate in it. I don't think that is a challenge which require a higher registration procedures. All challenges are free only, but you have to register yourself for these challenges. The COVID-19 challenge is a challenge with not much registration process, and the deadline is not yet came, so you will get plenty of time to do some research on this. So with this, I'm concluding my session, and I am sure that most of you have many doubts in your mind. So in the time permitted, if you have any queries, you can just post in the chat, and if I know the how to solve the query, or I know the answer to the queries, I'll uh, get back to you. So kindly post your queries in the chat session.
Ma'am, one query which came is
Yeah.
that 129 slices fixed or it can be customized?
I didn't get. Is this 129 slices are fixed
Fixed
or it
or
can?
it
No,
can be
no, no.
customized?
It's not a fixed set of slices or one. So you, I hope you are asking is the 129 is a fixed number, right? All the Nifty images are having 129 slices or not? That is the question, right?
Yeah.
Yeah, that is not a fixed slice. So the I mean, whatever the image that I showed is having 129 slices. There are MRI images with 30 slices. There are MRI images with 200 slices and all. It is not a fixed amount. So there are spacing in MRIs or spacing of pixels in MRIs. Based on that pixel, only this number of slices will happen. Spacing. So it's actually one slice, space between one slice to the next slice. I hope the query is clear. Okay, can you please explain about CUDA? Actually, I was about to talk and I think I have missed in my presentation. CUDA is for GPU processing. I told that we are using graphical processing unit for this deep learning algorithm. I guess somebody's noise is coming. Can you mute it?
One my question, ma'am. One my question.
I'll answer. I'll give answer to this
One my
question. Hello.
one my question, ma'am.
Ah,
One my
yeah.
question.
Yeah, yeah.
Now in India, very high medical sciences, but
Yeah.
for COVID-19 case failure, why?
I didn't get the COVID-19.
No COVID-19 case failure, why?
Okay.
More in vaccine creation very high period.
Can you type the question because I'm not clearly hearing. I'm not able to hear.
मैम वन क्वेश्चन मैं कहना चाह रहा हूँ इतना ज्यादा मेडिकल साइंस डेवलप होने के बाद भी इंडिया में
हाँ.
मेडिकल कोविड 19 के केस में फेल्योर क्यों दिखाई दे रही है मेरा यही क्वेश्चन है
So it's beyond my thing because it is completely medical related things, and I'm an engineer. I don't know much about this medicines and all.
मैम आई एम आल्सो मैकेनिकल इंजीनियर एंड एमटेक मशीन डिजाइनर रोबोटिक्स एंसिस
Shivaram,
programming is
please type your
already done.
question in the chat box.
Okay.
Yeah. So I was talking about CUDA, right? I was clearing the query called CUDA. I forgot to explain it in my presentation. CUDA is used when we need a graphical processor for our deep learning research. So this is a query from Salina Cheryl that I was explaining. So this CUDA processor is available. I have already told that it's available in the Google Colab, so we can use this for our processing. So the next is compute unified device architecture. So I don't understand how ma'am used it in the project. Can you please? I think the Selina is asking about the CUDA again, right? How ma'am used it in this project, right? So I have used this CUDA in this project because since it is a deep learning project, we need a CUDA processor. So the architecture details of this CUDA processor and all, I don't know. Next is from Shamla BV. Echocardiograph data set is available publicly. Any echocardiograph data set is. I guess there are some data sets available publicly for this ECG also. ECG signals I saw somewhere, but I didn't have much experience with this signals. I worked on images only, but I'm sure that there are echocardiograph images are available. For medical domain, would you suggest a pre-trained CNN trained from natural images or building a new model suited for medical image? I mean, isn't the negative transfer a problem? Would you suggest a pre-trained CNN trained from natural images? Actually, the most of the training CNN networks is using pre-trained model only. So the pre-training is happening with natural images only. In a deep learning, this pre-training will calculate the weights for a natural images, and the same set of natural images will be used for training the medical image. So that is a transfer learning problem. Okay, ma'am, did you use transfer learning techniques for training? Yes, that's what I am explaining. This is a transfer learning technique. Transfer learning means we will use a weight which is already trained using natural images or normal images, and that weight we will be using for training medical images. So the transfer learning is a very interesting topic, and you can if you are doing any medical imaging research, you can go for this transfer learning, because there are many interesting new topics are coming in transfer learning. So transfer learning is simply training a new network which is using a pre-trained network. So is there any other queries?
Any more questions? I am planning to wind up this session.
One more question is there. Did deep learning have more problem of overfitting than SVM and all? Yes, deep learning, the overfitting problem associated with deep learning is high. I don't know whether it is a generalized thing or not. In my experience, deep learning is having more overfitting problem than SVM or machine learning and all, because fixing a number of epochs for a deep learning is a very big task. So if the number of epochs are more, then there is a problem of overfitting. And if the number of epochs is not enough, there will be a problem of underfitting. So since this is a very small, fixing a very small number, the chance of overfitting is very high in deep learning compared to the machine learning problems. I'm not generalizing it, just from my experience. What I mean was,
we have time up. We need to wind up this session within
okay. So I guess all got some understanding of the Python libraries and research problems. I guess almost all the queries are also resolved, and thank you all. Is there any other things that I have to answer or something?
Hello, ma'am. One my question in chat box. In chat box.
Hello.
One my question in chat box, ma'am.
I think,
please answer.
Have I missed anything? Okay, thank you.
Any question ko chat box?
Thank you all.
One question.
Okay, then I'm going to wind up this session.
Okay.
On the behalf of the Rajagiri School of Engineering and Technology and committee members from this FDP, I'm really thanking Sri Lakshmi for having conducted a wonderful session in our FDP. So thank you, madam.
Thank you to you also for getting a chance to present my research problem.
You're welcome, madam.
Okay, I will share all the details with Akash sir, all the presentation and collab notebook I will share with Akash sir.
Okay.
Thank you very much.
Thank you, ma'am. Thank you. Dear participants, the next session we'll be having at 3:15 p.m. The Akash.
Welcome to CADMark World. CADMark Software, an ISO-certified organization incorporated in 1999, is a specialist engineering company with 15 crores revenue serving 700 customers with energetic certified team. Our mission and vision statement clearly emphasize by providing latest engineering software technologies to customers to build disruptive solutions for betterment of human life by being good stewards of the resources. With 20 years of rich experience, we implement software solutions along with our core services of CAD consulting, professional software training and 3D printing services. CADMark has emerged as one of the most promising engineering company in India and ready to deliver quality services to our clients. Let's have a look at solutions. CADMark partnered with global leaders to sell, support and service their solutions to drive customer innovation. We represent Autodesk for drafting and design software like AutoCAD, Inventor and Revit. As a Dassault Systems Platinum partner, we address areas of product design, styling, systems engineering, PLM solutions and realistic simulation. Accelerate performance and increase design productivity in 3D environment, thorough 2D and 3D mouse from 3D connection. Wide range of 3D printing solutions from MakerBot, a Stratasys company using fused deposition modeling. Finally, ExtraCAD, a product developed by CADMark, help in inspection report automation and ballooning software for AutoCAD and Inventor quickly and accurately. Our esteemed customers are our guiding force. Their valuable feedback helped us to make measurable improvements in our service. CADMark, India's first partner to sell 3D experience platform of Dassault Systems to VSSE for various successful space missions. Dassault Systems solutions are deployed in Cochin Shipyard for ship design activities while helping to grid analysis of defense equipments. We serve India Kawasaki Motors for their exclusive design of racing bikes in Pune. On the other hand, Hyundai Transys excels in seating and transmission. The world-class audio systems and cockpit design is created by Hyundai Mobis. Taking small steps in life sciences industry, Nymans uses Simulia for deep brain simulation. Forest Healthcare do 3D printing of eye testing machines, while Aster Metis Pro manufacture quality life-saving medical devices. Finally, our nation's pride academic institutions, universities, startup missions, government training centers create next-generation leaders, entrepreneurs and inventors. Our motto is to drive customer delight and grow with our esteemed customers. CADMark is happy to serve customers if provided with an opportunity. Come and explore our CADMark world.
United NDT is a pioneer institution which provides oil and gas, mechanical, and MEP courses to mechanical engineering students who want to get placed in top mechanical engineering core companies. We are an institution which is 10 years old and approximately 5,000 students have graduated from here, out of which 4,500 students have been placed in top engineering companies. The courses we do are expert in oil and gas engineering with TUV Ringland certification, diploma in oil and gas engineering, mechanical QA/QC, MEP, HVAC, and other international certifications like CSWIP 3.1, NIBOSH, AWS Certified Welding Inspector course, BGAS, NECE, etc. The certifications we provide for these courses are TUV Rail in German certification, ASNT Level 2 certification which is internationally accepted, STET Council certificate and NACTET which is approved by Government of India, and in-house certifications which are also valid worldwide, as we are an ISO 9001-2015 certified institution. Our faculty includes IIM graduates who take classes in project management, as well as pioneers in mechanical engineering field who have worked for companies like Saudi Aramco for 20 plus years. Our extensive lab facility is one of its kind and is revered by even our competitors. We guarantee 100% placement with feedback guarantee if you are not placed. For most of our courses and for the remaining courses, we provide placement assistance. Join us for a fruitful career and career advancement in mechanical engineering.
United NDT Training and Inspection Center, Palarivattam, Cochin.
BIRDS, Bioinstruments Research and Development Society, a forum for medical and engineering professionals to interact, identify tasks and solve scientific problems of mutual interest.
Engineering and technology is a part of the Rajagiri Vidyapeetham, a dream eternal being unfolded in time through the relentless CMI quest for excellence in the pursuit of wisdom.
Making the transition from school to college was especially difficult for me because I came from a different syllabus to most of the students here, but the faculty was really instrumental in easing the path. I think in other colleges, professors can be a little more aloof and they don't interact much with students beyond the actual lectures, but that's really not the case in Rajagiri. Our professors are really invested in our education and you really feel supported every step of the way.
An individual's personality defines his character. It is therefore required to nurture and mold it with the right formula in the right manner so as to make a person competent to face the challenges of the corporate world.
Right behind me, what I see is green and luscious area. You can see that all around Rajagiri, the greenery and also its different varieties of flowers. That's the first thing which struck me when I entered this college. Classrooms are equipped with very well designed smart classes. And libraries have so many e-journals which is offered to both staff and students get much more knowledge than they already have. In mechanical lab, we have various sections such as fitting, foundry, smithy, there's carpentry as well as welding.
With a trusted legacy in education that spans decades, Rajagiri School of Engineering and Technology is rated the best amongst the engineering colleges in the country. Located in the scenic suburbs of Kochi, Kerala, the institution offers undergraduate programs in 7 engineering disciplines. Applied Electronics and Instrumentation, Civil Engineering, Computer Science and Engineering, Electronics and Communication Engineering, Electrical and Electronics Engineering, Mechanical Engineering and Information Technology, and postgraduate programs in Communication Engineering, Computer Science and Information Systems, Industrial Drives and Control, Network Engineering, Signal Processing, VLSI, and Embedded Systems.
Rajagiri has always taken pride in its excellent academic records as well as a pool of talented individuals, molded with the right combination of commitment, discipline, and persuasion. And all of this has made RSET a top-of-the-list choice for some of the best and most reputed companies around the world. And of course, with the dedicated team of our placement cell, we have been able to pursue our dreams of working with some of the best corporates, both nationally as well as internationally.
Rajagiri has played host to various international conferences that brought together experts from different parts of the country and abroad for the sole objective of exchange of knowledge and ideas. Such an exposure has given us a very strong knowledge base in state-of-the-art technologies.
There is much more to being a student at Rajagiri than just going to your classes. You can get involved with a whole range of activities to help you meet new people, make new friends, and learn new skills.
We have been able to bring about successfully projects with boundless potential and which offer solution to real-time problems.
So wonderful years in Rajagiri has not just given me a great start to my career, but also given me lifelong memories to cherish. If you look at the beautiful campus, the days we walked around with my wonderful friends, and the great faculty who has helped us learn the tricks of the trade, using the best infrastructure that we can find in any college around the world, and also the best placement team that you can ever find in a college, helping us earn the right skill sets and also learn the ingenuity behind engineering so that we help our companies also deliver things better. Looking back on this wonderful years, I can only say one thing. This has been one of the most enriching and the best experience that I ever had in my life.
I walked into Rajagiri with a dream, and the immense learning experience the institution has offered to me has given me opportunities to carve my individuality and help me give my best to my chosen professional and personal assignments.
Rajagiri evolved into a premier technology and research institution, molding eminent professionals with creative minds, innovative ideas and sound practical skill, and to shape a future where technology works for the enrichment of mankind.
Dear participants, welcome back. In this session, I'll be introducing Dr. Kumar Rajamani sir. Sir, a warm welcome to you. Dr. Kumar Rajamani sir obtained his PhD in biomedical engineering from University of Bern, Switzerland. Currently, he is working as postdoctoral researcher at Institute of Medical Informatics, University of Lübeck, Germany. He is currently working on medical deep learning, significantly advanced architectures for medical image segmentation, COVID-19 lesion segmentation using attention mechanism. Prior to this role, Kumar was with Robert Bosch, GE Global, Philips Research, and Amrita University. He has obtained 9 patents to his credits. Now over to Rajamani sir for delivering the talk. Thank you.
Good afternoon, everyone.
Good afternoon, sir.
Should I be sharing the slides from my end or?
Sir, please wait. Akash will do.
Sir, if you can share, that will be great.
Sure, yeah. Can you see my screen now?
Yes, sir. Yes, you can see your screen, sir.
Okay, great.
So it's visible.
Okay, so play slideshow. I hope this should be okay. So can I get started?
Yes, sir, you can start.
Okay, so thanks a lot for the kind introduction and for the invitation to be part of this FDP program. I look forward for sharing some of my current learnings as part of the work that I'm doing on medical image segmentation. Though the slides per se are introductory, if there is interest at the end, I can walk a little bit through the advances in segmentation networks, which could potentially interest researchers working in this topic. And if there is further interest, we can interact post this session too. So the theme for this is medical image segmentation using deep learning. And predominantly the focus is on using UNets, which has become quite popular in medical image segmentation, not only in medical image, but also on general computer vision tasks also. UNets have played quite a significant role. But my primary focus is on biomedical image segmentation. And the slides I picked up from a couple of different sources. One, there is a nice video, a 5-minute teaser video on UNets to get started out on what is UNets. And from there, I've picked some of the content and also from another presentation. So it's all publicly available, these slides per se. So broadly, the topic would be on getting started, why we need UNet or how UNet came into play, and then some bits of how UNet initially was done with the data augmentation and what were their experiments. And in the end, some extending the UNet options, which are the ways to try it out on our data and so on. And I've also shared an IronPython notebook, and as time permits, we can run through that example that gives a more hands-on, I can't say a real hands-on, but at least a working example of, okay, I want to do UNet, I want to do segmentation and how to get started. So hopefully that IronPython notebook would help to get started for somebody new to this UNets or segmentation per se. So to start with, the historical background to this, I think since there have been multiple sessions on these themes, I think some parts would have introduced you already to deep learning and convolution neural networks. And convolution neural networks have predominantly now well accepted in specifically image classification tasks or making their mark in image classification, I would say. And that's primarily because you have 2-3 different things which have combined and come together. One, availability of large data sets like ImageNet, which has about 14 million or even more images. Then stronger compute that we have like GPUs, and nowadays you have GPUs that you can use on the cloud like Google Colab. And also this convolution operation, which helps to narrow down the field of view / processing an image in a more smart way rather than the earlier classical deep learning classical artificial neural networks methods where you do fully connected layers and so on. So we do this fully connected only towards the end, and initially they call it weight sharing, to look at a region in the image, convolve it, and then make it smaller. I mean, the make it smaller is through a process of max pooling. And then the convolution kind of helps to grab features, but the weight sharing happens even in the convolution. So you don't have so many weights like a fully connected network if you had to do. And that kind of helped gather features in an image, downsample it so that you only pick relevant features and not process the whole image. There's a lot of redundancy in the image. And then finally, at the end, I mean, these are repeating operations. If you see, convolution is to get features. ReLU is kind of nonlinearity. And then pooling operation is to reduce the size of the image. And then you repeat this multiple times. So you can kind of see the image decreasing. And that is indicated by the cubes becoming smaller. And the cubes are also becoming lengthier, you can see. And that is because the number of feature channels we compute are more. So we compute more and more features as we go smaller. And at the end, we take this, if it is a classification task, we just do a process called flattening to make it a single vector, and then do a couple of fully connected layers like classical artificial neural networks. And then you can classify them as whatever categories. In a computer vision task, maybe you want interested to know what object was it and so on. So that's the fundamental basis for CNNs, and convolutional neural networks have made large strides in making computer vision tasks, specifically classification, segmentation, recognition tasks. In fact, they are at a stage where they are even better than human performance, specifically like digit recognition and so on. And there are a lot of introductory material out there. I would recommend for somebody new to convolution neural networks this CS231N, which is from Stanford, for learning what is the convolution operation, what is the nonlinearity operation, and so on. And also some nitty-gritties of should you pad the image, because when you do convolution, you cannot convolve on the edges, so the image size will decrease. So if you want to maintain the image same size, you need to do some padding. There's another concept of striding. So do you convolve just stride 1, meaning just steps 1, or do you do stride 2? So you jump a little bit. Striding can also reduce the image size per se. And there are ways to compute what would be your output image size if your input was of a particular size and your padding is something and your stride is something. So there is a formula for how to compute your output size. And this becomes important if you are coding this layers grounds up yourself to determine what would be the size of the output image. And for now, we would rather move away from classification to segmentation. Classification are among the deep learning tasks slightly easier, if I may say so. So if somebody is new to deep learning, either on computer vision or on medical imaging, it might be a good idea to start with classification, because it's slightly easy, more manageable to say, okay, that's how the features are being computed, that's the fully connected layers and so on. But in medical imaging, after you do classification as initial to say, oh, something is diseased or something is healthy, you really want to go and find out where exactly is this disease per se, or anomaly per se or organ, where is it? And so this process is called localization, and that is the next step. After months, you get over classification tasks per se. So, I mean, there are three major tasks in medical imaging: classification, segmentation, and then registration. And I would put it in this way, that these are the complexities in which initially it's easy to do classification, then get to segmentation. And I mean, registration is slightly more complex, but there are lots of groups doing work on registration too. So when you do localization, we need to assign a pixel for each voxel location or pixel location, and we'll see some examples of this. So there are broadly two ways to do segmentation, and one is called object detection, which is more on the right that you see. You just want to put a box around a given object and say, here is the cat, and that's called localization. And so one can do a classification plus localization, and in this case you kind of learn these four boundaries of a given object and kind of do regression on these to find out where this object is. And there are networks in computer vision which does a very good job, like YOLO, you only look once kind of architectures, or Mask RCNN, which is also quite famous. RCNN was the initial version of it, and there's Mask RCNN, and there is faster RCNN, and there have been many progresses in that front too. So for those who are more interested in just doing box kind of region identification, these are the architectures which kind of help do localization. But in biomedical, the interest is not just to mark. I mean, one could do marking and say, hey, the doctor should pay attention to this region, but we could also go one step further and then mark every pixel to say this yellow is the cat, and every pixel gets this value for the cat, and then every pixel gets the background class for grass per se, and so on and so forth. So that's called semantic segmentation, and slightly more complex than localization. And there's also one more level of difficulty in this called instance segmentation, but I haven't seen, well, there are instance segmentation work in biomedical too, but predominantly I have primarily worked on semantic segmentation. And so these are examples in computer vision where you kind of do, yeah, these are all part of cow class, this is part of the grass, and so on and so forth. And when I meant instance segmentation, it is like this is cow 1, cow 2, cow 3, cow 4. Like you kind of go to that level of detail to really find out each instance, and that's called instance segmentation, right? I would, for those who are new to deep learning per se, classification or segmentation, also recommend this Fast AI course, which I got started about a year back on this when I was still part of Bosch and trying to get my hand on some bit of coding to do some quick, say, proof of concept that I can learn. And so this course really gets you in the philosophy of this course is coding first deep learning. So they don't teach you concept, they don't teach you what is CNN, what is ANNs, and what is ReLUs, and so on. They say, okay, here is some data, here is what I want to do, how do I get it done? And the course, the lesson 3 already jumps into getting you to getting UNet and taking some data and applying UNet on top of it. And in this session, we're going to see about UNets, but this is, the course is, Fast AI course is more driven towards computer vision. It's not biomedical, but for those wanting to learn computer vision and also get a perspective of it, also getting started with some code directly, I would recommend this Fast AI course V3. You can Google, there's a GitHub page, there's even a share your work kind of a blog where people share, I tried this worked, I tried this worked, and so on. So it's a very nice share portal where people share, and the videos are free for anybody to watch. The notebooks are free for anybody to clone and try it out. And in fact, my first paper on my own that I did on deep learning, more on the education kind of context, was using Fast AI about a year back. And it was very simple idea, but the Fast AI framework made it very easy to try it out, to do a fancy classification. It was a classification task. But just to finish the story about Fast AI, it has nice frameworks where you can just call UNet and you get a UNet architecture, and you can say what is there's something called a baseline model. We'll come to this, but maybe at the end of this session, you can bring this up again so that I don't forget. You can use any backbone model and make a UNet. That is specifically true for computer vision. You can use a VGG and make a UNet. You can make a ResNet and make a UNet, and so on. So in this case, they use a ResNet because they believe ResNet is pretty good for most tasks. So they take a ResNet, which is a residual network, and make it into a U, and then you can plug in whatever metrics you want. In this case, they say, I want accuracy, you can change, and so on. And then you get something called a learner, and you can then fit it for a few cycles. They also introduced this concept of learning finder or learning rate finder. And that's also one of the recent concepts that they bring in very quickly, introduce you. And I've also used this in my recent work, this learning rate finder and how to find the optimal learning rate and fit one cyclic learning rates, fit one cycle are all nice concepts that you learn within 3 videos of Fast AI. You get introduced into these concepts of classification, segmentation, regression, and so on. And then they jump into NLP and tabular data. I have not spent so much time on it, but that's how they progress this through. So coming back to what we want to do, we want to do semantic segmentation, and there has been some journey in semantic segmentation. Researchers have come up with different architectures and so on, but fundamentally, if you say what you want to achieve, if you use simple CNNs and you say, okay, I just want to find out every pixel, where it belongs to, whether it belongs to foreground, background class, and so on, it becomes quite a difficult problem, because generally images, even if you make them small, are at least to start with 256 cross 256. You can reduce it probably, but you don't want a small thumbnail which says where are the objects. You want it of native resolution, right? When I mean native resolution, you want the HW to be maintained at the end when you do segmentation, so that you know where the objects are. So you wouldn't do max pooling kind of operations. You just do convolutions to get features, and at the end do an argmax to kind of say which pixel belongs to which class. And you need H cross W predictions. When I mean H cross W, if you say 256 into 256, that many number of fully connected layers you would need to get, and I don't even know what is that number. It's a huge number that you need, and hence the number of parameters to be learned / the compute requirements, the GPU requirements, everything goes too prohibitively expensive that one cannot do semantic segmentation. Though the concept-wise it can be done, you just need too much of compute. So this was not a viable solution. So what then came as an alternative was, we do downsampling and make the image smaller and smaller, and not end there and just do a classification, but then we upsample this whole thing, and that's why it's called a U. So we systematically downsample and then systematically upsample, so that, I mean, here it doesn't look like a U, but in subsequent slides you would see that it looks really like a nice, I mean, there are some architectures which now work on VNet and so on. I don't know the difference between U and VNet, but yes, the philosophy is to go downsampling and then upsample, and there are some details. I'm not going through all the finer level details, but the important point is also these yellow lines, which are called skip connections. So data flows from the left of the feature channels to the upsampling part of the individual class information. So the network can gain information by information flowing through all possible ways. Right? We'll see one more example of it in the subsequent slides, how the skip connections work in UNet per se. And this is generally called an encoder-decoder architecture. And this part is called the encoder, and this part is called the decoder. And the speciality for UNet is the skip connection, but a lot of work is also ongoing currently on encoder-decoder architectures there's something called DAEs. There's also, meaning in multiple research fronts are going on using encoder-decoder architectures, right from adversarial networks, GANs, and finding latent representations and so on. But those are slightly more advanced topics. For today, we more focus on the U and having the skip connections and so on. But there's one should also know that it's very similar to this encoder decoder architecture, like auto encoders kind of framework. The first work, I don't know in what chronology order, but SegNet was one of the successful semantic segmentations. There's also a framework called FCNs, which just take the lowest sampling and just lowest layer. When you have the lowest resolution, you don't go sequentially upsampling, you just upsample it one shot and make it the original H cross W resolution. And that was how I think the chronology of how semantic segmentation evolved. FCNs became the first, then came SegNets, then came UNet, and then there have been some progresses. I don't know much about Deep Lab per se, but these are slides from our course we run at the university here, and I picked it. And so UNet became popular in 2015. FCNs were also around the same time in 2015, but UNet have now become more de facto. If your image is bigger and you want to really get precise segmentation rather than FCNs, we use UNets. We were using FCNs when I was working in Bosch for some eye image, retinal image segmentation to find where is the cup, where is the disc, to find glaucoma and so on. But FCNs have a place also if the image is not very big and your object you want to detect is not very big. But for most medical applications, I think UNet or variants of UNets have now been more regularly used, is what I would say. There are more details in the slides. I'm not going every detail, and the slides are shared with the organizers, so you can go through it in little more detail if you want. How can you do downsampling? How do you do upsampling? And variants of it and so on. And there are some references to papers which talk about, so there's a process called dilated convolutions. So you don't have to really do max pooling to reduce the image size, but your convolutions rather will take larger receptive fields, and then you can get the same effect of downsampling and upsampling. But again, it cannot be used everywhere, but maybe when the images are small, one can do this dilated convolutions, or in other words, atroz convolutions, as it is called, for semantic segmentation tasks too. So we now come to this is the prior work of FCNs, as I was briefly mentioning. You go through this convolution max pooling operation to systematically reduce the image size, systematically increase the number of feature channels, and these feature channels are written here. And finally, you have a very small image size, but large number of feature channels. And then you kind of upsample this whole thing to your image size. And then this is the FCN kind of way. But the segmentations are grainy, in the sense patchy. They won't be precise because you're just upsampling in one go. But this was the first motivation to do semantic segmentation. But the progress from there is to move to medical imaging, and the previous one was more on computer vision kind of segmentation, but biomedical imaging has more benefited from UNets. And the reason, again, this might be an overstatement. There are not many images, but the networks are having a lot of parameters. Usually you need a lot of training data. And well, now slowly medical also is now having a lot of data publicly made available. At the end of this session, maybe I would share with you some websites where you can get data with labels for your training your networks and so on. So we come to the UNet finally, with all this motivation set behind, and it was done by University of Freiburg. The group is, the person is Olaf Ronenberger. Ronenberger's UNet is how it is generally quoted in other references. And these slides are from the video. You can see this online, a 5-minute video which motivates and introduces you to UNet per se. And it's not very difficult. Initially, it may sound too complex, but if you really get into the implementation part of it, it's not very difficult, and one can realize this with a few weeks of effort. One can be up and running with getting the first units on your own data per se, right? So yeah, you don't need many annotated images. They in fact showed that they can even separate touching objects, which I haven't worked so much in my case where I'm working on COVID CT segmentation. I'm not separating the cells, so I don't really need that. But the initial worked on trying to separate the cells so that they are not touching and so on. And that was kind of one of the big successes for UNet 2. So we come to the UNet architecture to see why is it really a U, and so what you see is this is the input image. Some bit got cropped, but the input image has generally, we are not talking of RGB, and medical images are usually one channel. So that's why it's one. And this here is showing the dimension of the image. So we are working with around 572 cross 572 image size. And then we do convolution operations, and these are the arrows. And so you can see convolution and reluce are this. And since we do increase the number of feature channels, we immediately get 64. And then we do another convolution, and then we get another 64 feature channels. So usually we do this double convolution, then we step the image size down by a max pooling operation, and this max pooling is this red arrow. So the image drops by a factor of half. So from 500 it becomes 560, it becomes 284, and then we do another convolution, but this time we increase the number of feature channels. So now it is 128. And then we do the double convolution, so it's another time convolution 128. Again, we do a downsampling, so the 280 becomes 140, and then we do increase the feature channel, so it becomes 256 and 256, and then again we downsample this, so from 136 to 68, and increase the number of feature channels to 512. And this part is called the bottleneck, because the image slash features, I won't say image, the features have to go through this small dimension of 68 cross 68. And whatever is necessary information has to flow through this and then upsample to get the image back, right? So then from here on, these are this process is called concatenation. So the 512 is concatenated, and the 512 here is also added to it. So after convolution, whatever comes here is the blue, and the white part is what is coming from the left-hand side. So then it is concatenated. Then you do a convolution and reduce it to 512 feature channels, and then second double convolution, then upsampling. So those are the green arrows, so that the image size now becomes 100, and then 200, and then 400. So it's not native resolution like 572, but it is almost there, almost close to native resolution. One can also try to get to native resolution. If you do padding correctly, you would get the same resolution as input image back. And these white ones and the gray lines are the skip connections moving from the left to the right, so that the feature channels in the input image also flow into the right. When you estimate in the right hand side, you're not doing any classification. You want every pixel, whether it belongs to which class, but the information flowing from the left helps apparently to get this learning better done. So the skip connections also help in improving the overall performance per se. So the information can flow in any possible direction. That gives a lot more flexibility. And this is kind of the same philosophy like how residual networks were initially done. So information is not locked to say it has to move stepwise, chronologically, go down, go right, go down, and so on. Information can flow left to right, downwards, in any channel way it wants. It can flow, and whatever is most suited to get the best performance, the information flows. And this is kind of the architecture which worked well for after their experimentation. And in fact, there are a lot of papers have been written after this by changing the units and changing. There's something called unit plus and unit variants of several variants of it. But the start was this was what gave them great performance for segmentation. And finally, you have this in this case, it's 2 class, because if you just want background and foreground, but if you want multi-class, one can also have multi channels in the end. If you say I want 3 channels, then you have background, label 1, label 2, one can estimate that also. The downsampling is clear that you do max pooling. The upsampling you do by a process called, there are multiple ways. There is interpolation, bilinear interpolation to upsample. Then there is max unpooling. There is another way, then transpose convolution. So there are some 3 ways to do upsampling. And in some scenarios, A works better, some scenarios B work better, and so on. So one has to try interpolation probably, or transpose convolution. And for your, meaning each task is different. I mean, you will learn at the end, you would train this network to segment one object. It can't just work for any object you give it to segment and so on. But that also slowly people are addressing, so that you can train one network for multiple segmentation tasks. But at least when it started in 2015, it was more like, yeah, for a particular task, you train this and so on. And so if you're doing organ segmentation, some architecture would work better. If you're doing lesion segmentation, some other architecture. When I mean architecture, maybe you should do transpose convolutions, maybe you should do bilinear interpolations, maybe you should do trilinear interpolation, maybe you should do unpooling. So these are network configurations that one can change. And if you find a good network configuration which is novel enough, those are also potentially publishable for your problems that you work on. Maybe you have a specific data set and you want to try out. It's not easy. Such architectural changes to bring in novelty is not easy. But if you do find some ways to improve slash a context of a problem which works better, those are already potential publications one can do. And so it's good to be aware of various kinds of downsamplings, various kinds of upsamplings, various kinds of non-linearities one can apply. Like ReLU is not the only non-linearity. There's something called parametric ReLU. There's a leaky ReLU. So there are so many network, I won't call it hyperparameter, network configurations one can change. And depending on your problem and based on maybe current literature, you could find out what would work for a given context and try it out. So that's broadly how UNet is. I hope it is slightly better in terms of the understanding. I have already explained what these numbers on the top are, what these numbers on the bottom are, and what these arrows are in terms of convolution. And there are some visual representation of what you do in a convolution. And we do multiple such convolutions. So we get multiple feature channels, right? So the X and Y are your dimensions of your image, and this axis, Y, this increases the number of feature channels. So if you do one convolution, you get one feature channel, and then you do one more, and then you get another feature channel, and so on. And these weights for the convolution are shared. So you have only one convolution kernel to convolve around the whole image for this first feature channel. And then that's why it reduces the number of weights to be learned or unknowns to be learned in the deep neural network. Right? So every such convolution operation is usually followed by a nonlinearity, and that nonlinearity is generally ReLU, which only keeps the positive side of the values intact, and the negative sides it truncates to 0. There are, as I mentioned, there are other variants of these nonlinearities that one could explore. There's parametric ReLU, there's leaky ReLU, and then in fact there's a recent ReLU that I came across called attention ReLU, and those seems to be also giving better performance on some of the classification segmentation tasks. So the other operation is this max pooling operation, which downsamples the image, and that visually, if you say you take a 2x2 region, or it could be even larger, it can be a 3x3 region, and you take the maximum value of that region and put it here. And so that operation reduces the image by 50 by 50%, because for every 2 you get 1. So the X resolution will drop by half, the Y resolution will also drop by half. And that's one way to reduce the image size. that's another way to increase the receptive field. A receptive field is how much a convolution is able to see in the original image. So if your image size shrinks, your convolution is able to see a larger region of the image. And if you shrink it again, the convolution is able to see the larger region. And finally, maybe as you go really down, your convolution can probably see the whole image at one go and then say, oh, I know this image is, if you're doing classification, maybe part of a cat or a dog example per se, right? So that's the unit architecture. There's a contraction part of the unit. There is an expansion part of the unit. And I presume by now you would have understood this much more better. They say increase the what and reduce the where. And for those who have worked with convolution neural networks, you would know that there is this uncertainty principle. You can't know both what is important and where is it and so on. So as you make the image size smaller, you don't know where that information was, but you more understand features about it to well represent, right? So the contraction kind of reduces where it is. I don't know where the lung is or where the organ is per se, but I know good features about it to find out whether it is healthy or not. So that's the contraction part, but this unit kind of complements it and then says, don't worry that we lost where it was. We can increase via the expansion path and also find out where it was. So even though you reduce the where by this match pooling operations, the upsampling part compensates for it, and you still can reasonably find out where the object was. And that's what we want in semantic segmentation, right? And then I was also mentioning about this, what do you call, information flowing from the left to right, concatenation, right, feature concatenation that one does. And this also helps in getting better segmentation performance. And these are called skip connections. The word was not coming right away. And that's one of the novelties in the unit when they initially proposed that these skip connections helped get better performance. So you would see these white in all these regions in getting this information from the left. As I was mentioning, the upsampling can be done in 3 different ways. One is up convolution. So you take every value and map it to 2x2 region. So that then increases the image by a factor of 2. One can do interpolation, bilinear or triennial interpolation, and then say interpolate it in the surrounding regions in this image for me. And there's also called transpose convolutions, which also does similar. So each does it in a slightly different way, but the effect is the same. We want the image to be, visually it's not rightly represented, it's not the same dimension. The image's resolution becomes bigger as you go up via the up convolution part, right? Usually it is 2x2 because you don't want to replicate it in bigger regions. Take one value, replicate it in 3x3 might be making it patchy, blurry. So you do it 2x2. So if you see transpose 2D and 2x2 kernel size, then that's the up convolution part for your unit, right? And then finally, these are the output classes, how many labels you need, and then you get the corresponding segmentation output. So that kind of finishes broadly the theory part of what the unit does. The architecture for it, the ways to downsample, ways to upsample, skip connections, and so on. And the rest of these slides are more showing results where they achieved when in 2015 they did units. So they applied it on electron microscope images, and these images are very large. So they even proposed doing a tiling operation. So you do small region, you segment it, and then you go to the next and you segment it, and so on. So you can do tile-wise multiple places and then get the segmentation for the whole image. And they also did data augmentation, which helps in having smaller number of data, but still training your network to be, I can say, generalized better, not overfitting to the training data, and so on. So this data augmentation is taking an input image and deforming it slightly, and then use that as another training data. And so every image that you have, generally, when you do data augmentation, one can create synthetic data. One can also do this deformations, and The code which we would see in the end has small snippets of code to do this data augmentation. This is nonlinear deformation, but you could simply do translation, rotation, scale as simple deformations. But in this, they in fact went to grid-wise, taking it and finely deforming each grid. But if you look at the image in totality, the image would have had nonlinear deformations in total. And those are nice ways to increase your your training data size per se, and most effective solutions will have some form of data augmentation as is appropriate. I mean, you cannot take an image and then make it upside down, and maybe such images may not occur in medical context. So it has to be justified that such augmentations don't create unseen data or unrealistic data. That's the right word, unrealistic data. But if that is the case, then you can do some amount of data augmentation. And as I mentioned in the code sample, we would see some examples of it. The other major thing was they also did some variants to the loss function to make cells so that they don't touch each other. This is very specific to EM electron microscope images and the context of its segmentation. I have not worked on such specific details, but for those who are interested, they can look up maybe how they did. They also share how they did that by putting a loss for each pixel in the boundary, and then say it has to belong to some one of the classes, or it should be far away from both the classes, or some such mechanism. I think I had a slide with the loss, but no, it's not there. But if you look up the original video or the Ronenberger's paper, you can see how they ended up putting some, though that's also one form of novelty. If you really want to bring in novelty for your problem, what is the major issue? How can you put in a loss function to realize that for your work is also a way of contribution for new research and new publications per se. So modifications can be network architecture, modifications can be in loss function novelties based on what you want to achieve, can be also in smarter optimization methods or learning schedulers that you can come up with. So there are many ways to come up with publishable work and so on. This was an earlier challenge, and in 2012, I think one could probably get these data sets. I've not tried them specifically to search whether these data sets are still around, but ISBI is one of the famous symposium on biomedical imaging, conference on medical imaging. This year, the submission is due in October. So if somebody is interested to work on something for SB, that's already a good conference to think if somebody is working on medical. I should also mention SPIE, SPIE medical imaging is also having a good amount of traction, a lot of people submitting early results and so on. And that deadline is in this month, another 10 days, we have SPIE's deadline. But anyway, they publish their work, meaning there's also challenges at each of these conferences. And for those who want to get started with some data, you can pull the data from the challenge, see the results, and then try to work on it to make it better. But they addressed 2-3 different problems, or the challenge was to address 2-3 different problems, low contrast regions, and then fuzzy membranes, which is not clear, and then structure within structure, like other cell compartments within a structure and so on. But they got a good score by doing their unit architecture. They did a further challenge in 2015. I think this was earlier, right? 2012. And then this is 2015. They had tracking an object and better segmentation by unit and so on. So that's the summary for some of the results what they achieved. I mean, this is not what is from my end. It's more sharing what they could achieve. But in terms of extensions for where this could be is one could extend this naturally for 3D. It's slightly more harder to work with 3D. But there has been already work people are doing directly on taking 3D and training on 3D labels and producing 3D. So it could be semi-automatic where you could train with few slices and then the network learns for the remaining, or it can be end-to-end fully 3D segmentation. And the only thing is the requirements for GPUs goes quite higher in terms of number of GPU RAM that you require. Handling the data also becomes slightly harder in terms of preparing the data. You may not be able to pass the whole 3D data through, so you may have to do patch-wise if it is a big organ. So there are challenges. If it is a small organ like this, I don't know what organ is this, probably small intestine or so. If it is a small organ, it's easy, but if you're segmenting large structures, then it's very hard to fit the whole data in the RAM or in the GPU RAM. And so people have come with architectures where you take block-wise 3D and process it and then stitch them together. But the architecture kind of remains the same. One can take the same unit, but then do, instead of 2x2 convolutions, you do 3x3x3 convolutions. So you kind of convolve in the Z direction. So you have an image which is 3D, and then you can convolve in the Z direction also. And then your max pooling also does reduction of size in 3 directions. The up convolution also happens in 3 directions, and so on. When I mean 3, X, Y, and Z. So you have a cube block that you process at every step. Slightly difficult to visualize, but once in terms of code differences, it's very minimal. It looks more fancy, it looks more nicer for people to read that, oh, you're doing 3D segmentation. But again, I would not directly jump into 3D right away. If it is good, you're starting with UNet, it is better to start with 2D and get comfortable with it, and then jump to maybe smaller structures to segment in 3D. Right? And there are a lot of use case scenarios where they have shown that UNet performs better than even doctors. This is a case of OCT images, and there's a paper in Nature Medicine which was recently published where they say this UNet or deep learning performs better than even a retina specialist, and how are they able to do it and so on. But that's also one more context where people are applying segmentation approaches, taking OCT images. I mean, there are many scenarios for doing segmentation. So that kind of finishes my slides for the theory part of it. And then you can see the advantages and disadvantages. So I was mentioning, you have to train it for every separate task. It's not one shot, but it gives very good segmentation results and so on. And last but not the least, I would, for those who are more going towards deploying a solution / giving a solution for a startup / industry / deploying this, there is this architecture called NoNewNet, and they have done a very nice mechanism to, it is there for 2D, it's there for 3D, and they do some kind of network configuration, network hyperparameter tuning, which network model would work the best, and so on. And they kind of are able to showcase very good performance on most segmentation tasks. And in fact, there's a website which I would share, but for research purposes, this is quite complex. It's difficult to work with it, and you cannot innovate on top of it easily. So I wouldn't use it practically for most say network discovery / loss function discoveries that you want to do. But if it is just showing high numbers, I think the NoNewNet is a good place to go and then check out the performance. And the philosophy was NoNewNet bet the performance of every other UNet variant. There were several hundreds of papers which came after UNet saying, we made change. But then NoNewNet came and then leveled the ground, saying all these changes is not required. A simple UNet will work if you know how to get the network properly orchestrated / the hyperparameters rightly tuned and so on. Then you can get the best performance just with a simple UNet. You don't need fancy UNets per se, right? So that's the end of my slides. I hope it wasn't too fast a run through. if there is questions to be addressed, we can do that now. If you say we go through the code, then I can walk through the code, and later we can take the questions then.
Sir, better to go to the code first.
Okay, sure, done. So then let's jump to the code part of it. And before I go, I just wanted to share the medical, NNUnet per se. And there's this website called Medical Decathlon, and one can get data sets for multiple medical image work here. And for anybody working on medical segmentation, I would recommend this as the one of the places to check out if you have good data sets that you can get. And if you, yeah, already at the results page, probably. Yeah, so they kind of made it one place for all kind of segmentation, right? So you have brain tumors, you have liver tumors, you have brain segmentation, and so on and so forth. So you can see multiple contexts of segmentation tasks that they have made them popular. I think the download is not too difficult. You could download this from Google Drive, and you would be overwhelmed with the amount of data that they provide in terms of multiple organs, multiple modalities, and so on. And the other thing, which is also what I wanted to mention, was the NoNUnet, which I was mentioning briefly, gets the best score across these organ segmentation. So most often you say DICE as one of the scores, which is intersection between your ground truth and your actual segmentation output divided by the union, and the higher the DICE score is better. So across this brain tumor segmentation, the heart, the hippocampus, the liver, lung, pancreas, prostate, you can see NNUnet being consistently performing best and having rank 1. And there are other methods mentioned below. And there are different other challenges that they have kind of quoted, and that's not the only place where NNUnet has been proven to work very well, but that's one place to see why NNUnet is really good, and so on. But this website I just wanted to share so that you are aware that there is medical data that you can download and play around with for any of your works that you want to do. The other website that I want to mention is about this md.ai. For our code, we'll be taking data from here. You need to create an account, and once you create an account, it's a free account. You can also get some token for the code. I put my token so that you can you can run the code directly. But when I was preparing slides for this or looking through the code, I realized, there is in fact nice data sets they have provided which are recent. So there is COVID-19 data provided, which is, I guess, there is some description about how many images they have provided. I was just reading through this and seeing that also. So they have provided quite some, I don't see that right away, but you can, there's a show more, but yeah, link to the original data set. So if you can go there, then you can see where is the data set, what is the size of it, and so on and so forth, and links to download, and then right away you can download through this. They made start very easy, and I think they also provide the lesion markings. So it is not just plain data that they give you, they even give you maybe markings of it, some description of it is there, what markings they have provided and so on. I've not gone through, but it's about 300 images or so or more that they have provided. I'm not using this data currently for my work, but this is also one such data set one can utilize. So this portal integrates md.ai, has multiple features. This has a feature for doctors to do markings. It has a way to share publicly data available in some way. You can also pull from your notebook to a Colab notebook data from this portal. So in many ways, this is a nice, I chanced to come across this md.ai when I was making a presentation about a year and a half back, and then I wanted a simple example where people could play with, and so they also give collab notebooks, so that made it easy for my presentation when I was talking about segmentation and so on. So we come to this notebook example, and as I mentioned, this notebook is given as an Iron Python notebook. I've sent it to Akash sir, and with Hari sir I've shared it. And I've also shared the Colab page. So probably you could also run it directly on Colab. But if there is any difficulties in doing so, I mean, an Iron Python notebook, you would have to upload it to your Google Drive and then open it. I presume some of you would be already comfortable with Iron Python notebooks and Google Colab interface. And so I assume at that level we get started. Otherwise, I would have to then explain what is Colab and so on. So there is this connect which you connect to a cloud computer, and then you are given a system with GPU in the cloud that you can utilize, and you also have provided some disk space and some RAM to work with, right? And then there's a brief introduction of what this data set is about. It's a lesson that they have. They have multiple lessons. And so if somebody wants to get started on classification, you can look at those. You want to start on segmentation with lung x-rays. That's what we are doing today. There's also pneumonia detection, and then there is pneumonia detection, some 3B. I don't know the difference between this is Kaggle data, this is maybe some other data that they have, and each of them have Colab links, so you can open it in Colab and hopefully run it without problems. There are some small changes to be done because it's not really recent. I had to do some changes because there's a difference between Keras and TensorFlow Keras. This code is in TensorFlow Keras. I am not very conversant with TensorFlow Keras myself. I use more of PyTorch per se, but the broad overview of the code should be followable if you just run through the code. I am not expert in explaining each line of code, but you can get some idea of it. So as I mentioned, MD.ai has a nice annotator page which can annotate data. So this is more for, I mean, MD is more for doctors, as the website itself says. So you can go to this, and it has tools for doctors to annotate. I have not played with that a lot. And I have not gone through the other Python client also per se. For me, it's more about demonstrating a scenario, and we can get directly started. So once you're connected to the cloud PC, there is, if you want a new code block, you can press code and you get a new code block. And if you want to run any Python level code, you can just say NVIDIA/SMI to know what kind of GPU you have been allotted now. And you can see that currently you are given Tesla T4. It has 15 GB of GPU provided, and I mean, each time it's different. Sometimes they give you 12 GB, sometimes they give you 16 GB, and so on. But the good part is you are given a GPU to work with, and so it's a great facility provided by Google. I mean, there are others also who provide this, like Kaggle has its own framework, but most people use Google Colab. And so the other thing is you can, right, usually it is now set to using GPUs. Earlier you had to go to runtime, change runtime type, and then say, I want a GPU. There's also something called a TPU, which is a tensor processing unit, but we are good with GPU. I've not done TPUs myself and so on, right? So that's just to say, if you want to, so any command, if you want to run Linux, this is a Linux box that is provided in the cloud. So if you want to run any command like ls to list the directory, you just type it out, press shift enter, and then you can see the output coming below it, and the output comes right away after the command, right? There's also some things on the left that you see here, and there's this block with like a folder, and this helps you to upload any data you want, which can then be used in your Colab. So if you have your own data set lying on your hard disk, either you can push it to Google Drive and then pull from Google Drive. I'm not going to walk through that example today, but it is possible to connect Google Drive and Google Colab. And so any data you have, You can push it to Google Drive and then connect your Google Drive to Colab and then pull data. But if there's another option, you can upload data with this button. You can just say upload any data from your local system, and if you are having data that you want to work with on your own, you can do that, and this data will show up here. And then you would have to fix the directory paths to pull the data appropriately, and one can then utilize your own data also, right? So we briefly run through this code chunks. The important part is to look at how do you get a unit and how do you train a unit to do segmentation tasks. We are not getting into the specifics at this stage of how to modify a unit, because that will then get you started out on, oh, I want to try my novel ideas and so on. That is one stage higher, and you would then need some more level of control on TensorFlow, on either TensorFlow, Keras, or on PyTorch, and then understand architectures and be able to modify it. But the objective today is to broadly walk you through a framework for getting started on UNet for doing some segmentation, and B, running it through in a TensorFlow framework. But those who are further interested can then play with the architecture, change the architecture either in this or in, I would also share some resources for PyTorch at the end of it that one can do with. So the first block is to install this MDAI, and pip is a installation utility on Linux systems, and you can then say what version of MDAI I have, and it prints the version. And MDAI is more a library which also has, I mean, md.ai is the website, but MDAI is also a library, which has some nice utilities, right? The utilities are pulling the data from md.ai, doing some kind of data preparation if you want, and so on. So they give some facilities. I don't know all the facilities, but it gives you some. And as you get more familiar with MDAI, I think one could also look up MDAI GitHub page and see more information about it. Practically, it should be. So if you Google MDAI and GitHub, I am pretty sure you would find a GitHub page for it. And there's a project file, oops, maybe not the right, probably this too. This also is the same. These are ML lessons, the client, yeah, maybe this one. I don't know, but maybe I shouldn't divert at this stage, but there is definitely, because you're able to clone and use, one should be able to find the MDAI and see some information about it. This also looks very similar, right? So they walk you through a hello world program, and then, oh, there's also a FastAI introduction, and then these 4 examples I was talking about. And probably there is more documentation which you could find in these GitHub pages, and it is not just, yeah, if you go to the home page, probably you could, yeah. So that's the GitHub page I was trying to look up. And then there is also a documentation page. They talk about the annotator. So if somebody is a doctor or interacting with a doctor and you want help in doing annotations, they can take a look at this as one option. And then there are some other examples also. So coming to our example, we create a MDAI client, and we need to give this token. Currently, this token is my token, which I had created as a user account on MDAI. And with this, you can pull data from there. And then we say, get me this project, because it's a solved example. There is a known path where there is some project file, and we just say, go pick it. I mean, this is for those who are smart enough. You can change the data to your own data and so on, or work with some other data from MDAI. But for now, the intent is not to focus so much on the data per se, but is to more focus on where is the unit, how do you train a deep neural network, and so on, right? So in this case, we still are using this MDAI. If I say P is initialized as MDAI client, right, dot project. So that P is a variable, which is the MDAI client project. and it has been initialized with this project from lesson 2. And so if you say, show me the label groups, you then see that it is having one object called lung, and its ID is some ID. But generally for most deep neural network training, you need them to be an index, which is a number, or so you convert this into, meaning we map this to a 1, right? So you cannot train a network by saying lung and then say background and so on. You need numbers for each category. So 1 now means lung and 0 means background, right? And now we can say, show me the data set. What is the number of elements in the data set per se? I'm just clicking through, not going. So there are 138 data sets available for you. And in fact, this data set also has a link that you can directly see. It's there in the same page. So it gives some explanation about, oh, this has 138 X-ray images, 80 of them are normal, 58 of them are abnormal. So you can see what is the distribution and so on. And that link for it is shared somewhere above. It says, if you want, defines, somewhere it mentions where is the data set for this. Yeah. So yeah, somewhere there is a mention for this. Yeah, I think so. Okay, we'll skip for that. You have a link for that, or later I can send you the link for the data set. Okay, so now we have the data ready, and then we want to visualize some of the data. And again, MDAI, the same package gives you facility to, one can use matplot and plot the images, but these are more helper functions to see the images. Okay, so these are the images I have. And then you want to now get to the point of creating a unit and using a unit. And the good part is Keras itself has an inbuilt variant of a unit, and that's Keras unit. And so we get this TensorFlow 2 version installed. We install Keras and Keras unit. We import the libraries like NumPy. CV2 is OpenCV version 2. Matplotlib is for plotting and so on. And then this is just a helper function to load images. I am not going into detail, but it goes through your current data is in some data structure. Let me put it that way. It's in a dictionary format. And so you run through in a for loop, and then you kind of take all the images, resize the image to 128 cross 128, because the resize shape is 128. You can resize it to whatever size you want. You are doing some padding to add some zero padding so that all the images are of same size. And then you, in the end, have images and masks. And image means your X-ray image, mask means a ground truth learning label image, which has zeros in the background region and 1 where the lung is, right? So you have these two. So you run this helper function load image. Oops, I have not yet run that part of the code. So you run that. So every code chunk needs to be run so that you can prove. If you get any error, you should be able to debug it also. That improves your coding skills as you work with it. And then you come to next to just show some random images to say what are the images looking like. And so these are sample images. These are the ground truth. So this is marking the region where the lung is for this image, and the region is marked as 1 and the background is 0. And I think the third plot is, yeah, applying the mask on this image probably, right? So this is the training data we have: input image, input labels, and so on. And this is what we feed into the network, right? An image and its label we feed into the unit, so that, well, we don't feed the image and the labels together. We feed the image on the left. On the right, when we get the output, we compare it with this labels. And then if it is wrong, we propagate the error backward, right? And then again, it does a segmentation. We check, oh, it's wrong. Again, we propagate it back, and so on, right? So this is used for estimating how good your network is learning and so on. And finally, how good your network is performing. Also, we use these ground truth labels per se. And there are these helper functions. This is a very good helper function from SK scikit-learn, which splits the image into train and test, and we can say what is the percentage of train and test split you want. So if you say 20%, 80% is training and 20% is testing, and so that gets you already this X train, X val, Y train, Y val. So then X train, X val is used for your training, and to estimate your performance, you use Y train, Y val, right? For those who are used to machine learning, this should not be too much of a difference. For those who are new, it may take a little bit of a time, but yeah, it's the easiest way to split a data randomly into train test splits and so on. And one can also do some cross-validation with train test splits. It's a nice function that you have. And then we get to this part, which is augmentation. I was mentioning about data augmentation. In our slides, we saw about randomly rotating, translating the image. So in this case, we rotate the image by some random rotation. Well, rotation range is 180, but it can rotate anywhere between 0 to 180. We do some height shift, width shift, shearing, zooming, and so on. So it's simple saying what is it you want to do, what extent you want to do, and then do you want to pad the regions, because if you rotate the image, then some regions becomes void. You don't want to fill it up. Can you horizontally flip? Should you do vertically flip? Should you do, and so on. So it's a very simple set of commands, and then you get the required achieving data augmentation that you need to do. And you could look at the documentation to see are there other ways to augment, right? So this is Keras utils, and if you look at the helper function, you can then see more possibilities of doing augmentation. Then we come to this unit, and as I mentioned, Keras itself has a custom unit, so you don't have to worry. You just say, get me a unit, and then your unit is ready, right? And then you say custom unit, oh, what's your training data? X train you're giving. And then we use batch norm, yes, number of classes. You have to say, am I segmenting one class, two class, and so on. This filters, I really don't know. Probably it's the number of filters that you initially want to estimate, I guess, but I'm not very sure. You have to look at the documentation. Regularization, there are many ways to do regularization. One of the methods is called dropout. And then finally, you want output to be mapped into 0, 1. And so you need some activation function for it. In this case, we use sigmoid, right? That's it. And so if you do this, you have your unit ready. But then this only gives you the flexibility to define the unit, which is already, use a defined unit already there. You don't have any control on, hey, I want to change some layer. I want to change the 7th layer, not to have 64 channels, but to have 128 feature channels. I want to do one more downsampling, right? Those you cannot do because this is pulling definition from predefined. But if you get better at coding, you can then go into it and still modify. I'm not good at Keras TensorFlow, but in PyTorch, I know how to do it. But once you learn how to do this, you could be able to change it. But for now, what I made changes little bit from the earlier was, I made the code run because it was not directly running. You need to change to TensorFlow Keras. B, I've also done some printout so that you can look at the model. So there is a model summary, and we have printed this model summary. And this should give an understanding of what the unit is. And if you have understood broadly the unit from the slides, then this should not look very different, right? What are we starting? We're starting with an input layer. The image size is 128, 128. It has one channel, okay? Then we do a convolution. The input to the convolution is from the input, and then it creates 64 channels. And then the number of parameters is 576, yes. And then we do a batch norm, because usually you have this convolution, non-linearity. We also do a dropout. So we'll see the non-linearity also coming somewhere down. And then we also do this. Now it's more recommended to do batch norm as it improves overall performance. There are different kinds of normalization. You can do batch norm, you can do channel norm, you can do instance norm, and there is in fact a medium page which talks about this different kinds. But this predefined model does batch norm. And so here nothing changes. It's still 128, 128. It's just doing normalization to adjust the values between a particular range. Say, let the mean be 0, let the standard deviation be 1. That's one kind of normalization, right? Then we do a dropout, and dropout is just dropping some of the network connections, so that is not full everywhere there, but it doesn't change any of your network dimensions, so it is still 128, 128, 64, and you can pay attention, it all takes input from the previous layers. Then you do a convolution, so that's the double convolution, so it again maintains it at 128, 128, 64. Number of parameters again we can see, and then we do again batch norm, and now comes the first max pooling layer. So we have done 2 convolutions, that's why we call it the double convolution, and then we do a max pooling, and you can see the image reduces from 128 to 64, and 64 cross 64. Then we do another convolution, increase the number of feature channels, so it then goes to 128, and then so on and so forth. I mean, so we do this again, double convolution, again we do a max pooling, reduce the image size, again double convolutions, again max pooling, so 32 becomes 16, and then again so on and so forth, until we come to image size 8, and that's the bottleneck where we get to. And then once we get there, then we do the upsampling part, and in this case we do converse con transpose 2D to upsample the image, so the 8 becomes 16, and then we do this concatenate, that is the skip connection to concatenate, and then we continue this process of upsampling the image. So you can see it goes from 8 to 16, 16 to 32, and 32 to 64, and 64 to 128, and here we have come back to the native resolution. We are not losing resolution because we are doing some padding. We are not seeing the code, we are just looking at the architecture. And finally, it also prints what is the total number of parameters, what is the total number of trainable parameters. And these are interesting attributes you can put into your paper when you write. We are using a unit, we use this many number of trainable parameters, and so on and so forth, right? So that kind of defines the architecture of the unit. And if you really look at the code, it should not be too difficult. Even the description for such a unit is not very difficult. Maybe we don't have enough time today so that I can walk you through a code of how to write your own unit, but it is not very difficult. And since we, again, coming back to one of the questions which I reminded, we are not using a backbone of a RESTnet or a backbone of a VGG. When I mean a backbone of a RESTnet, we will use 34 layers to downsample, and that's what is RESTnet 34, and 34 layers to upsample, right? If you use that, that's called a RESTnet backbone. Here we are doing a custom unit, which is not having any predefined backbone, but we are defining so many 3-4 downsamplings and 3-4 upsamplings, and we are done with that unit. There is also one more nice visualization which I saw when I was reading through the documentation, and you can do a plot model, and that is from a GraphVis library, and that's already pre-installed, and it gives you a slightly different visual representation for the whole model, and you can see, oh, that's how the convolutions, batch pooling is happening, on and so forth. Where are the skip connections going from the top? You also have these skip connection lines going down all the way and connecting it to some other layer. It's slightly difficult to view the whole thing, but it gives you some other visualization for the whole thing, right? So now we come to the unit training part, and this I wouldn't spend too much time on. The main part is you need an optimizer. In this case, we use an Adam optimizer. We need a loss, so we use binary entropy loss, binary cross entropy loss. We need some ways to measure the accuracy. In this case, we use accuracy and IOU, intersection over union, which is like a die score, if I may say so. And if you say model.compile, and I think model is where your unit model is, and now you say, I want to use this optimizer, this loss, this metric. And so here is also ways to bring in your novelty. You can change different loss functions which meet your requirement, write your own loss and bring it in, bring your own different variants of optimizers and so on. And once that is done, model.fit starts training the network, and this does training for 10 epochs, and each epoch it does it for 100 cycles or 100 steps per cycle, and your data is, well, it knows it is using xtrain. The validation you're using xval, yval. If you remember, we use train test split to split between training and validation. So we use this validation so to print the validation scores, because you also want how good the model is doing on not only on training data, but also on validation data. So you would also get outputs like saying what is the validation loss, what is the validation accuracy, what is the intersection over union, but also what is the validation intersection over union. And you would see that this may take a little bit of a time, maybe 5 minutes, but in 5 minutes your training is done and you would see that one should not rely too much on the accuracy, because accuracy is misleading, because background is a major class. I mean, lung also occupies a major percentage, but if you're segmenting smaller structures, then you can get 95% accuracy very easily just by saying everything is background. So the other important metric is IOU, the intersection over union, and that is that you can't get very high scores easily, because you have to get the lung precisely correct, the background precisely correct, and this is not a tough problem, lung segmentation per se in X-rays. So you would also see IOU coming to 87% or so quite easily in 10 epochs, and one can also train for a larger number of epochs per se. So once this is done, you can then plot your metrics, and then it will plot your training accuracy, validation accuracy, training loss, validation loss, and these could also be inputs. If you want to write your paper, you can take this out and put it. And finally, some visualizations to say, show me the outcome segmentation. So that's the input image, that's the ground truth, that's the predicted outcome, the predicted lung segmentation. So if you can see, performance is reasonably, I mean, there are mistakes, it's not 100%. I mean, it goes all the way down here, it's very fuzzy. So it kind of not learns that fuzzy regions, and hence the score, die score, no, IOU scores are only at around 87% or so, and not 100% or 99% and so on. So there are ways to improve, and there are advanced architectures that can be done on top of units. Like I'm currently working, as I was introduced in the beginning, I'm working on attention systems. So you can take attention systems and put into units and make the units better. And there are various attention models, and so there are a lot of avenues to do interesting research without too much difficulty. There is umpteen amount of data given, umpteen possibilities to work with, and now the training is finished, your IOU is 88. So if you have some mechanism to improve the IOU, that's your contribution, and you can then make your publication with that, and then you can, I mean, I plotted it from 2 because there was some issues earlier. I can as well do everything because there was some high loss score and the plots were not doing well. But if you, yeah, even now it is having such problem. The initial start is very high for the validation loss. So then the plot masks the whole output. So it's very hard to view, but yeah, that's, then it's slightly more visual that you can see it's decreasing, what training loss, validation loss is decreasing, the accuracy is increasing, and so on. And you can finally get your custom segmentation outputs. Yeah. So yeah, you can see there are mistakes. It's not 100%, and that then gives us scope and room for improving. I mean, and that's where further research can happen. So I am at the end of the
So one question one of our audience has raised, is data augmentation enough to solve data scarcity problem? Can you please address this?
Yeah, is data augmentation enough to address data scarcity problem, you mean?
Yes.
Okay, yeah. Yeah, I'm seeing the chat also now. Sorry, I initially didn't pay attention. Now I see that. Yes. So yes and no, right? It is one way to increase your data size. It's one way to make your model more robust to newer scenarios. It cannot be the only solution that one can use. In fact, now a lot of research is happening on using adversarial networks to create synthetic data. So if you look at GANs and synthetic data creation, people are able to create synthetic medical images, so data augmentation is only one way to address the scarcity problem. Now the current, there's a recent conference which happened called Medical Deep Learning, MIDL, medical imaging deep learning, and there are a lot of papers there where people worked on GANs and such frameworks for synthetically creating data. So that's also one mechanism one can use.
I think
Should
there
I
is a
just read through
request to share the Golang link. So I hope
Yeah.
you're sharing that to us towards the end.
I have already sent the collab link to both Akash sir and to Hari sir.
Thank you.
Sorry,
Then
to Akash primarily, and yeah. So
we'll be circulating things. Thank you, sir. Then any more questions from the participant side?
well, I see some questions on the left.
Yeah, you can
drop
please
out.
if it is possible.
Yeah, so one question is dropout is used to reduce overfitting. Yes, that's true. It's kind of regularization mechanism, and there are many regularization mechanisms. Batch norm already does some kind of addressing for it. Dropout was 1 or 2 years back more actively used. Now it's not too much, but yeah, but it's one way to reduce overfitting. That's true. Then there is a question on augmentation results in loss of information from medical images. I wouldn't say loss of information. You have to only make sure that you only create legitimate variations and not unrealistic variations. If they are realistic, it's fine. You don't generally do blurring, but you can even do blurring so that the network becomes robust to such scenarios. See, your whole point is network should learn all kinds of variants. So if it is blurry and it learns from it and is able to perform on blurry scenarios, then it's better. It's not that it's only going to look at blurry images. It's going to look at blurry also, right? So it's one way to make the network robust, right? Can you use a unit pre-trained on CT images for a segmentation task on ultrasound image? Does this change in imaging modality affect the accuracy? Yeah, sure. I don't think you can use unit trained on CT to do ultrasound. This is called domain adaptation, but domain adaptation is more done on modality. There are some research work trying to do this, learn on CT, do on MR. And so on, multi-model learning. I am not so much working on it per se, but it cannot be done directly. You have to do some kind of adaptation to make it work. Whatever I have shared at this level of know-how, you wouldn't be able to directly train on CT and apply. You have to train on ultrasound, it will work on ultrasound. Or you have to train on CT and ultrasound, then or you have to convert one modality to the other. So some such tweak has to be got in, otherwise it won't directly work. Okay, so a couple of more questions. Can we run neural networks that uses CUDA like GPU in normal i5 processor systems? So I don't know whether this question is for a desktop scenario or on a collab scenario. If you are doing collab, it provides you a GPU, so I don't think this question is relevant. So maybe the question is running on a desktop. Yeah, whichever, if you can fit a GPU, if you have a GPU handy in your desktop or laptop, you can use that. The more the GPU's capabilities, the faster will be the training. The bigger the RAM, more data you can fit. Faster meaning better the GPU, faster will be the training, things like that. But yeah. Doesn't using downsampling and simultaneous upsampling in unit take up more time and memory? We should have larger GPU capacity, right? So that was one more question. Yeah, maybe people who asked those questions have also dropped out. So am I just running through the question for the sake of questions? I don't know.
No, sir, can you please share your email ID so that we can also interact with you?
Sure, yeah. So in the chat window, I'm sharing my email address. And yeah, there was one more question, which is good, Colab or Anaconda Navigator. So if you, Anaconda is more for if you have your, if you have a system with GPU and you want to locally code on your laptop or desktop, then Anaconda is better and you can install. But installation takes a lot of effort, setting up CUDAs, UDN, TensorFlow, the right versions, and so on. So it takes a lot more effort to do all this. But if you have the interest, you can still do. For early starters, it's better just to start with Colab and get started with it.
Any more questions, please, from the participant side?
Limitations of Colab. Okay, so somebody wanted to know. Yeah. So 2-3 things. One, Colab will time out, right? So if you are training a network for several epochs and you go away from your system and it senses that you are not actively there, it will disconnect, and then you wouldn't be able to then save the results per se. So it's better to connect it to Google Drive, save the intermediate results. And some of my students who are working / colleagues, I would say, who are working with me, have learned to work around these limitations. But yes, one of the limitation is it doesn't give you all the time the same kind of GPU. Sometimes it will give you 16 GB GPU, sometimes it will give you 12, sometimes it will give you 8. It depends on what is available, they'll give you. Second, it times out. When I mean time out, if you're actively on that page and doing some work, then it will stay alive. If you get away from it for 15-20 minutes and then come back, it can time out and then disconnect, and then the results are not persistent. It's a cloud system, so if you're disconnected, the results are gone. So Google Drive is persistent, whereas Colab is not persistent. So if you have intermediate results, like you have a trained network, there's something called snapshotting. So you can save a snapshot and push it into Google Drive, and then the drive will save that result, right? But those comes with slight amount of playing around, experimentation. I'm using desktop with GPU cards here in my university, so I'm not using so much of Colab per se. But I have my Bosch colleague who was interning with me. Now he is working with me doing some work. He is using Colab extensively and he is able to do it. It needs some amount of working around, but there are limitations, but it can be worked around. And if I imagine 2-3 years back when we had to set up GPUs on the cloud with Azure or with Amazon, AWS, I mean, those were far more difficult days. These are all gone with Colab. I mean, you have a Google account, you need a Google account, and then you're almost good to get started. Yeah,
okay, then thanks to all for participating. We have come to the end of the session. On the behalf of Rajagiri School of Engineering and Technology, I am thanking Kumar Rajamani for sharing with us the knowledge that he has gained. And thank you, sir. Thank you, sir.
Okay, thank you.
Thank you, sir. Sir, you may leave.
Okay,
No problem. Okay, thank you.
Done.